Hello, my dear students. I hope you all are really doing great. First of all, I welcome you all on this amazing platform of PhysicsWallah. Students, in the second lecture of chemistry in this champion series, mainly for JEE mains and NEET aspirants, today we are going to discuss a very important chapter of organic chemistry, and that is isomerism, a highly important chapter. Students, mainly in organic chemistry, we are having three most important chapter. The first one, GOC, we have covered it. The second one, isomerism, and the third one, reaction mechanism. These three chapters are basically the backbone of organic chemistry. If these three chapters are crystal clear, I'm 100% sure you will not face any problems in the subsequent chapters like hydrocarbons, alcohol phenol ethers, carbonyl compounds. So just go through this lecture very sincerely, and I request you, once you have gone through this lecture, attempt all the PYQs of JEE mains as well as NEET, and do mention in the comment box whether you were able to solve all the questions or not. I'm 100% sure, and I can even bet after watching this lecture you won't face even a single problem in any questions of JEE mains and NEET. So students, let us start our discussion. So students, now let's start our discussion on isomerism. How do we define it? The compounds having the same molecular formula but different physical and chemical properties. Such compounds are referred as isomers. I am having two compounds. The molecular formula of the two compound is same, and if they are having different physical or chemical property, then these two compounds are nothing but isomers of each other. Now let us talk about the classification of isomers. We are having two different types of isomers. One is structural isomers, other one is stereoisomers. Let us first of all talk about structural isomers. The compounds having the same molecular formula but different structural formula, same MF, different structural formula, or we can say different IUPAC nomenclature. Different IUPAC nomenclature. Such compounds are nothing but structural isomers. If I talk about the classification of structural isomers, students, structural isomers are basically chain isomers, position isomers, functional isomers, metamers, tautomers. One more type of structural isomers is there, although I have not mentioned here, but you can write it. That is ring chain isomers. Ring chain isomers. Right? So this is all about structural isomers. We will discuss each and every structural isomers in a detailed way. Now it's time to first of all introduce stereoisomers. Students, the compounds having the same molecular formula, same structural formula, but different arrangement or orientation. Different arrangement or orientation of atoms or groups in three-dimensional space. Such compounds are nothing but stereoisomers. If I classify stereoisomers, basically it's of two types: configurational isomers, conformational isomers. It's of two types: configurational and conformational. And if I further divide this configurational isomers, students, we are having two different types of configurational isomers, that is optical isomers and geometrical isomers. The third one is conformational isomers. Now we'll discuss this stereoisomers in a very detailed way. We'll talk about everything: optical isomers, geometrical isomers, conformational isomers in a very detailed way. But first we are going to start with structural isomers. Let's start our discussion on structural isomers. Right? Structural isomers are also referred as linkage isomers. They are also referred as constitutional isomers. Linkage isomers or constitutional isomers. Let's move ahead. First, let us talk about chain isomers. The two compounds having the same molecular formula but different parent chain length or side chain length. Compounds having the same molecular formula but different parent chain length or side chain length. Such compounds are basically related as chain isomers of each other. They are nothing but the chain isomers of each other. Talking about this chain isomers here, they should have the same nature of functional group, multiple bond, or even the substituent except this alkyl group. Means the functional behavior should not change. The functional group, the multiple bonds, all these things, if two compounds are having the same functional group, same number of multiple bonds, and even the same number of substituents and everything except alkyl group, and now if they differ in the parent chain length or side chain length, then these two compounds are chain isomers of each other. Okay, let's try to understand it with few examples. I'm having C4H10. It's nothing but n-butane, right students? Okay, now can I write it like this? CH3, CH2, CH2, CH3, right? Okay. Can I write it like this also? CH3, C, CH3, H, CH3, right? Let's check 1, 2, 3, 4. 4 number of carbon atoms. How these two compounds are related? Is the molecular formula same? The molecular formula is same. C4H10, C4H10. What's the parent chain length here? 3 member carbon, 4 member parent chain length. Right here, the parent chain length is consisting of 4 carbons. Here, the parent chain length is consisting of 3 carbons. So, how these two compounds are related? They are nothing but chain isomers of each other. Chain isomers of each other. Let's take few more examples. I'm having C6H14. Okay. Let's draw the different possible chain isomers of this particular compound. Can I draw it like this? I can have 1, 2, 3, 4, 5, 6, right? Students, now what I am going to do? I am going to decrease the parent chain length by adding substituents, right? Now, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. The parent chain length consists of 5 carbon. Now I am having 1 substituents. Okay? One more thing. Can I write it like this also? Parent chain length consists of how many carbons? 4 carbons. How these two compounds are related? They are nothing but the chain isomers of each other. How these two compounds are related? If I number it as 1, 2, 3, 4, how these two compounds are related? 2 and 4. They are the chain isomers of each other. Chain isomers. What about 3 and 4? Are they chain isomers? No. 3 and 4 are not the chain isomers of each other because here the parent chain length is same. Right, students? So, I hope you understood the basic definition of chain isomers. Let's take few more examples. I can have compound like this. I'm having CH2, CH3, right? And can I do it like, write it like this? How these two compounds are related? They are nothing but the chain isomers of each other. I hope you understood what do we mean by chain isomers. So students, now let's talk about the second type of structural isomers, and that is position isomers. How do we define it? Two compounds having the same molecular formula, the same parent chain length or the skeleton chain length, but they have different positions of functional group, substituents, or even multiple bonds, then these two compounds are related as position isomers of each other. The two compounds having the same molecular formula, the same parent chain length or the skeleton chain length, but different position of functional group, multiple bonds or substituents in the same skeleton, right? Such compounds are basically the position isomers of each other. Here, in once again here also, in position isomers also, the nature of functional group means the functional group should remain the same, right student? One more thing, and one of the most important thing, in the definition part only I have told you, in position isomers, the skeleton of carbon atom should not change. The skeleton of carbon atom should not change. Then let's take few examples in order to understand this concept, positional isomers. Okay, I'm having a benzene ring, right? Here one group CH3 is present here and one more CH3 is present here. We know this position is ortho position or 1-2 position. Now, the same benzene ring, the same molecular formula, but now this CH3 is present at meta position. One more, I'm having CH3 and now this CH3 is present at para position. How these three compounds are related? 1 and 2, they are the position isomers. Ortho is the positional isomers of this meta 1 and this meta is also the positional isomers of para 1. So both 1, 2 and 3, they all are position isomers of each other. Let's take few more examples. Next one, I'm having C, single bond C, single bond C, double bond C, right? It's nothing but but 1 in. Now C, C, double bond C, C. It's nothing but but 2 in. How these two compounds are related? They are nothing but the positional isomers of each other, right students? Okay, I'm having Cl, 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 Cl. How these two compounds are related? Once again, the position of substituents is different, right? And if the position of substituent is different and the parent chain length is same, molecular formula is same, then the compounds are related as positional isomers of each other. Positional isomers of each other, right? Okay. Can we take few more examples? Let's move ahead. I can have C, 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 OH, right? And I can have C, 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 OH, right? Okay. If I name it, can I say it's nothing but 1, 2, 3, 4, 5, pentane 2 all. And it's nothing but 1, 2, 3, pentane 3 all. Pentane 3 all. It's nothing but pentane 2 all. How these two compounds are related? Once again, they differ in the position of functional group. The parent chain length or the skeleton chain length is same. So these two compounds are positional isomers of each other, right? Okay, I hope you understood this positional isomers. Now let's move to the next type of structural isomers, and that students, now let us discuss the third type of structural isomers, and that's nothing but functional isomers. Students, if I talk about this functional isomers, we can simply define it like this: the compounds having the same molecular formula but different nature of functional group attached to them, then such compounds are basically related as functional isomers. Let's take few examples in order to understand functional isomers. I'm having, let us assume, a compound with molecular formula CnH2n plus 2 O. Can you tell which all compounds may have this molecular formula? Either alcohol, or ether. So how these two compounds are related? They are the functional isomers of each other. Let's put n equals to 3. So I'm having C3H8O. Okay. Now if I write, can I write it like this? CS3 CH2 CH2OH. What's the molecular formula? C3H8O. Can I write it like this also? CS3O CH2 CH3. Right? What's the molecular formula? C3H8O. Now, what's the functional group present here? Alcohol. What is the functional group present here? Ether. How these two compounds are related? They are the functional isomers of each other. So alcohol and ether having the same molecular formula but different functional group, right? Different physical and chemical properties. These two compounds are functional isomers. Let's take few more examples. I can have the compounds with molecular formula CnH2nO. Which all compounds may have this particular formula? Let's take n equals to 3. So C3H6O. Okay. So which all compounds may have the formula C3H6O? I can have CH3, CH2, C double bond OH. So what is this particular compound? Aldehyde. Right, students? Okay. I can have CH3, C double bond O, CH3. What is this compound? Ketone. Is the functional group same? Not at all. Here the functional group is aldehyde group. Here I am having a keto group. So they are the functional isomers of each other. Having the same molecular formula, they are obeying the formula, or they are having the general formula CnH2nO, but the functional group is different. One is aldehyde, the other one is ketone. So aldehydes and ketones are functional isomers of each other. We can have more compounds. We can have unsaturated alcohol also. Let's see. CH2 doubly bond C single H, right? And then I can have CH2OH. Can you tell me the molecular formula here? 1, 2, 3, right? So I'm having the carbon number 3, hydrogen 2, 1, 3, 2, 5, 1, 6. So unsaturated alcohols. Even we can have few more. Cycloalkanol, cyclic alcohols. They will have the formula like this only. Let's see. What's the molecular formula here? C3H6O. So C3H6O. So if I talk about all these four compounds, aldehyde, ketone, unsaturated alcohol, cyclic alcohol, we can have even cyclic ether. This one will also have the same molecular formula, right? CH2, CH2, CH2O. So C3H6O, right? We can have even unsaturated ethers. So all these compounds are having the general formula CnH2nO. So aldehyde, ketones, unsaturated alcohol, cyclic alcohol, cyclic ethers, they are basically the functional isomers of each other. So if someone asks you what may be the functional isomers of aldehyde, you can say ketone, you can say unsaturated alcohol, you can say unsaturated ethers also, you can say cyclic alcohol also, and you can say cyclic ether also. But student, now in general we consider only these two as the major functional group. So if I am having the molecular formula CnH2nO, most of the time what you will see aldehydes and ketone cases only. So aldehydes and ketones, they are the functional isomers of each other. Let's move ahead. Acid and ester. Acid and ester. how these two compounds are related. They can be the functional isomers of each other. How? Let's see. I can have the formula CH3, CH2, C double bond O, OH. What's the molecular formula here? C3, H, 32516, C3, H6, O2. Right, student? I'm having C3, H6, O2. Okay. Can I write it like this also? CH3, C double bond O, O, CH3. What's the molecular formula still here? C3, H6, O2. The molecular formula is same, but here the functional group is ester. Here the functional group is acid. How these two compounds are related? They are the functional isomers of each other. We can have few more cases. Cyanides, isocyanides. We can have CH3, cyanide, and isocyanides. Isocyanide. They are also the functional isomers of each other. CH3, C triple bond N, right? And we can have CH3, N triple bond C, right? How these two compounds are related? They are the functional isomers of each other. Functional isomers. Cyanide, isocyanide. We can have nitro orthonitrito, O nitrito, right? Let's see. Nitro nitrito. I can have CH3 NO2 and I can have CH3 ONO. Right, students? How is the molecular formula same? Yes, but they differ in the functional behavior. They differ in the physical and chemical properties. So these two compounds are functional isomers of each other. Can we have few more cases also? Definitely. Different degree of amines, 1 degree amine, 2 degree amine, 3 degree amines. They are nothing but the functional isomers of each other. Let's take one case. CH3, CH2, CH2, NH2. Okay. It's nothing but 1 degree amine, right? 1 degree amine. Now, can I write it like this also? CH3, CH2, N, CH3, H. Is the molecular formula still the same? 1, 2, 3 carbon, and everything is same. So molecular formula is still the same, but this is a 2 degree amine. Now, if I look at the physical properties of these two compounds or even the chemical properties, 1 degree amine and 2 degree amine will have different chemical behavior. So how these two compounds are related? They are the functional isomers of each other. One more case. I can have even 3 degree amine. CH3, CH3. The molecular formula is still the same. The molecular formula here also is still the same, and this one is 3 degree amine. So 1 degree amine, 2 degree amine, 3 degree amine, they are nothing but the functional isomers of each other, students. I hope you understood this one also. Let us move ahead. I can have this phenol CH3, right? And now what I am going to write, I'm having CH2OH. How these two compounds are related? One is aliphatic alcohol, the other one is aromatic alcohol. Aromatic alcohol, aliphatic alcohol, right? How these two compounds are related? They are also the functional isomers of each other. Aliphatic alcohol and aromatic alcohols are also the functional isomers of each other. I hope you understood this one also. Students, if I take few more examples related to this functional isomers, the best example is the case of hydrocarbons, mainly in the cases of alkenes and alkynes. There also we are having functional isomers. How? Let us see. What's the general formula of alkene? The general formula of alkene is CnH2n, right? CnH2n. Okay. So let's see, take C4H8. Okay, C doubly bonded C and C, right? This is the skeleton. But1in. What is the molecular formula of this compound also? Is it cycloalkane? Is the functional behavior different? Yes. Compounds having the same molecular formula but different functional behavior, they are nothing but the functional isomers. So can I say this alkene and cycloalkane, they are the functional isomers of each other, right? One more case. I can have alkyne. What's the general formula? CnH2n minus 2. Let's take this particular case itself, C4H6, butane, right? This is butane. What is the molecular formula of this compound? C4H6 only. Okay. What is the molecular formula of this particular compound? C4H6 only. So what are the functional isomers of alkyne? Alkadiene. The functional isomers of alkyne can be cycloalkene. The functional isomers of alkyne can even be a bicyclo compounds, right? Like this. I hope you understood this also. So students, let's summarize all the functional isomers cases. First, we had discussed alcohols, and alcohol was having the functional isomers ether. Then we had aldehyde. The major functional isomers is ketone, although we can have unsaturated alcohol, cyclic alcohol, and like that. But mainly the functional isomers of aldehyde is ketone. Next we have acid. The functional isomer is ester. Next we have cyanide, isocyanide, nitro, nitrito. Then we have amines, 1 degree amine, 2 degree amine, 3 degree amine. Then we have aliphatic alcohols and aromatic alcohols. Then we have alkene, cycloalkane, alkyne, cycloalkene, alkadiene, and even a bicyclo compounds, right? So I hope you understood this functional isomers. Now let's move to the next type of structural isomers, and that is metamers. So students, now let's discuss the next type of a structural isomers, and this structural isomers is nothing but metamers. How do we define it? The compound having the same molecular formula, same functional group, but different alkyl chain length connected on either side of the functional group, then the compounds or the isomers are metamers of each other. Let's go to the definition part. Okay, students, when two isomers have the same functional group but have different nature of alkyl and aryl group connected to a heteroatom, and the heteroatoms are mainly oxygen, nitrogen, sulfur, then these are referred as metamers or metamers, right? Okay, students, mainly in case of keto compound we don't consider metamers, right? So let's start with ether case itself. I'm having CH3, CH2, CH2, O, CH3. Okay, I'm going to write one more compound, CH3, CH2, O, CH2, CH3. Now let's check these two compounds. What's the functional group present? Ether. Functional group present ether, right? Okay, what's the name of this particular compound? Methoxypropane. What's the name of this compound? Ethoxyethane. Yeah, diethyl ether, right? Okay, is the molecular formula same? Yes, molecular formula same, functional group same, functional group same, but can we say on either side of the functional group the alkyl chain length is different? Here I'm having alkyl chain length of 1 carbon, here I'm having 2 carbons, right? So how these two compounds are related? They are nothing but the metamers of each other. Let's take one more case of ester. I'm having CH3, C double bond O, O, CH2, CH2, CH3. Perfect. Let's write one more compound. I'm having CH3, CH2, C double bond O, O. How many carbons? 1, 2, 3, 4, 5. CH2, CH3. Now, on the right side of this functional group, I'm having a propyl group. Here, I'm having the ethyl group. Will the IUPAC name be same? The answer is no. Right? Is the molecular formula same? Yes. Is the functional group same? Yes. Functional group same, molecular formula same, but on either side of the alkyl group, on either side of the functional group, the alkyl chain length is different. Here I am having a chain length of 3 carbon. Here I am having a chain length of 2 carbon. So how these two compounds are related? They are nothing but metamers of each other. Right, students? So student, it's all about metamerism. We have one more type of structural isomers, and that is ring chain isomers. Let's discuss that also. So students, now let us discuss one more form of this structural isomers, and that is ring chain isomers. Okay, let's write it. Ring chain isomers. The compounds having same molecular formula, having same molecular formula, but differ in the sense of ring form or chain form of the structure. Okay, let's take one or two examples in order to understand this definition in a better way. I'm going to take one hydrocarbon alkene, C6H12. Can I say it's nothing but alkene, and having the general formula CnH2n, right? Okay, I'm having C6H12. Can I write it like this? 1, 2, 3, 4, 5, 6. Right, students? This compound is having the formula C6H12. Can I say this one is also having the same molecular formula, but one is a open chain compound and the another one is a cyclic ring? One more case. The same molecular formula. One more case. The same molecular formula. One more case. The same molecular formula. All these compounds are having the same molecular formula, right? One is an open chain compound, all other are cyclic compounds. So how these compounds are related? They are the ring chain isomers of each other. Now even in the ring also, all are cyclic structure, but in every structure, the parent chain length of the cycle or the size of the cycle is different. Even these two compounds are ring chain isomers of each other. These two compounds are ring chain isomers of each other. These two compounds are ring chain isomers of each other. So all these compounds are basically nothing but ring chain isomers of each other. Students, I hope you understood this ring chain isomers also. Students, now it's time to discuss one of the most important structural isomers, that's nothing but tautomers. First question, what do we mean by the term tautomerism? Let's first of all define it. Students, compound having general formula, having general formula C single bond H, single bond X, doubly bonded Y, always exist in dynamic equilibrium with its another form which will have the general formula C doubly bonded X single bond YH. Always exist in dynamic equilibrium with the one more form, and that form is having the general formula C doubly bond X single bond YH. Now these two forms are basically referred as the tautomeric forms of each other. Let me write that. C H X doubly bonded Y always exist in dynamic equilibrium with one of its more form, and that particular form is C doubly bonded X single bond Y H. Okay. Student, now you will say, sir, what do we mean by X, Y, and what are the different conditions for a compound to exhibit tautomerism? We'll discuss one by one. Let's start our discussion. Student, if I write this general formula, C single bond H single bond X doubly bonded Y in equilibrium with one of its more form, and that form is C doubly bonded X single bond YH. Generally, this X and Y are relatively electronegative elements. This X can be C, N, O, and this Y generally N, O, S. The electronegativity of Y is somewhat greater than the electronegativity of X in general. Okay. Now, this particular carbon which is connected to X is referred as alpha carbon. Alpha carbon. This carbon is generally sp3 hybridized. This carbon is generally sp3 hybridized. The hydrogen connected to it is nothing but alpha hydrogen. We have studied these things in hyperconjugation, right? The carbon which is a neighbor of sp2 hybrid carbon is referred as alpha carbon, and alpha carbon containing hydrogen is nothing but alpha hydrogen. And we have studied alpha hydrogen is relatively acidic in nature. So this hydrogen is going to be acidic. We have studied in hyperconjugation, for a compound to exhibit hyperconjugation, the presence of alpha hydrogen is mandatory. Similarly, for a compound to exhibit tautomerism, the presence of alpha hydrogen or the presence of acidic hydrogen is mandatory, right? Students, in tautomerism, basically there is an oscillation of this acidic hydrogen from C to Y. You can see it. There is oscillation of this acidic hydrogen from C to Y. Now let me take a few examples so that you can understand it in a better way. I can take CH3, C doubly bonded O. First of all, can you tell me which species is X here and which one is Y? Can you tell me? Student, simply you need to remember this formula. C single bond X. C single bond X. So can I say it is going to be X? And then this is going to be Y. Right? Now, what is the another tautomeric form of this particular compound? Will it exhibit tautomerism? Let's see. X doubly bonded Y. X doubly bonded Y. C having at least one acidic hydrogen. Here I am having 3 acidic hydrogen. So this particular compound will definitely exhibit tautomerism. And if it will exhibit tautomerism, can I write the acidic form? What I am going to do, I am simply going to remove one acidic hydrogen from here and put that acidic hydrogen on Y. Let's write that CH2. Now C single bond X. Here I will have C double bond X. So doubly bonded C. Now single bond YH. Single bond O. And simply the migration or the oscillation of this acidic hydrogen from carbon to oxygen. So can I say it is going to be the tautomeric form of this one. It is going to be the tautomeric form of this one. Student, obviously if the tautomeric form is there and these two compounds have different functional group, so we are going to name these compounds also. Can I say it's nothing but carbonyl compounds? Students, always keep it in mind while doing the tautomeric questions. All the carbonylic carbon you need to say that as keto. Whether it is aldehyde or ketone, we'll name it as keto compound. We'll name it as keto compound. Now this one. Can I say it's nothing but alkene? And what is the suffix of alkene? Ene. Can I say it's nothing but alcohol? What is the suffix of alcohol? All. So can I name this compound as enol? Right? So if a carbonylic carbon is having alpha carbon, that alpha carbon is having alpha hydrogen, then this particular compound or this particular keto compound will exist in dynamic equilibrium with one more form, and that form is referred as enolic form. Okay. Now the second question which you may ask from me, so why do tautomerism exist? What's the reason? What's the driving force for this tautomerism? Student, if a process is occurring, if a process is spontaneous, obviously there is something responsible for it. And here the driving force for this tautomerism is nothing but intermolecular hydrogen bonding. How? Let's see. I'm having keto form. No doubt I am having a monocarbonyl compound C double bond O, and this molecule is relatively stable, highly stable. C double bond O, this is monocarbonyl compound. But if I draw its tautomeric form, then I will have enol COH, right? Now student, can I say between keto and enol, I can have intermolecular hydrogen bonding. Intermolecular H bond. And because of this intermolecular hydrogen bonding, can I say the stability of keto compound will somewhat further get enhanced. So in order to increase the stability, this keto compound exists in dynamic equilibrium with one of its more form, and that form is enolic form. Will only keto compound exhibit tautomerism? No, any such compounds which is having acidic hydrogen and which is obeying the general formula CH single bond X double bond Y will exhibit tautomerism. Any compounds having the general formula CH single bond X doubly bonded Y will exhibit tautomerism. I hope you understood it. Now let's practice some questions in order to brush up this concept. Let's move ahead. Students, now let's start our discussion of these questions which are there on the screen. Which of the following compound will exhibit tautomerism? And if the tautomeric form is possible, even we need to write the tautomeric form also. Okay. For tautomers, what we need to check? Compound having the general formula CH single bond X doubly bonded Y. Okay. C connected to X doubly bonded Y, and here I am having hydrogen also. Can I say this carbon and this carbon as alpha carbon, and can I say here I am having two hydrogens, right? So I am having acidic hydrogen, I am having X doubly bonded Y. So is the tautomeric form possible and feasible? Yes. This particular keto compound will show tautomer. What will be the tautomeric form? What I am going to do? Here also I am having alpha hydrogen. Here also I am having alpha hydrogen. From one of the side, I am simply going to remove one alpha hydrogen and I will simply attach it over oxygen. Right? Now the tautomeric form will be, let's do it from the left side. C single bond X. Here I will have C double bond X. Single bond Y H. Right, student? This one is the keto form. This one is going to be the enolic form. I hope you understood this one. Next one. Well, can I say name this as keto? And can I name it as enol? Let's move ahead. Moving to the next one. Students, can you name this particular compound? The compound having the formula CWR, CW bond NH, such groups are referred as imine group. Imine group. We name it as imine. Now, will it exhibit tautomerism? Is it fulfilling the criteria? Can I name it as X? Can I write it as Y? So I'm having X doubly bonded Y. I'm having alpha carbon. Alpha carbon is containing alpha hydrogen. So alpha hydrogen is also there. X doubly bonded Y is also there. So C single bond X double bond Y will exist in dynamic equilibrium with C doubly bonded X. So I will have C. I will remove one acidic hydrogen. So CH2 doubly bonded N. CH2 doubly bonded C. C doubly bond X, single bond Y, N, oscillation of one of the acidic hydrogen from carbon to nitrogen. Already one hydrogen was there, one more hydrogen will get added. Right, student? Yes, one hydrogen is there also. Right? So this is going to be the tautomeric form of this particular imine. Can I name it? Can I say it's alkyne? And this one is amine. What is the suffix of alkene? The suffix of alkene is -ine. And the suffix of NH2 is amine. So in plus amine, enamine. Can I say it as enamine? So what is the tautomeric form of imine? Enamine. Right? Let's move ahead. Will it exhibit tautomerism? Let's see. I'm having X, perfect. This one is Y. This one is going to be the alpha carbon, let's assume. But this carbon is sp2 hybridized. sp2 hybridized carbon cannot be the alpha carbon, right? And here we don't have any alpha hydrogen also. So this compound will not exhibit tautomerism, no tautomers, right? No tautomerism. Why? No alpha H. Let's move ahead. Will it exhibit tautomerism? Will this particular compound show or exhibit tautomerism? X doubly bond Y. This carbon is going to be the alpha carbon. Why? sp3 hybrid carbon containing acidic hydrogen. Okay. So will it exhibit tautomerism? Let's draw the tautomeric form. Okay. The tautomeric form, C single bond X double bond Y will have the formula C doubly bonded X single bond Y H. Now student, you only tell me, will this compound exist? Can I say this compound is anti-aromatic? Anti-aromatic. And anti-aromatic compounds are highly unstable compound, right? So will this compound exist? No. The basic or the driving force of tautomerism is to increase the stability. If it is getting converted to a highly unstable compound, will this process occur? Will this process be spontaneous? Not at all. So no tautomers. Sorry, just a minute. Let me draw first of all this and then no tautomer. No Tautomerism. I hope you understood this one also. Okay. Now this one. CH3 N doubly bonded O. I'm having here alpha carbon, alpha hydrogen. This one is X, this one is Y. C single bond X, double bond Y. We'll have the formula C doubly bonded X, single bond YH. Right, student? 2 hydrogen. Now, this particular group is nitro group. So we say this compound as nitroso compound. Nitroso. This is not nitro. This is nitroso. Nitroso. And the tautomeric form of this one, C doubly bond N single bond OH, is referred as, this particular group is referred as oxime. So nitroso always exists in dynamic equilibrium with one of its more form, and that particular form is referred as oxime. C double bond N OH. Oximes are having the general formula R C doubly bond N single bond OH. I hope you understood. So, student, this is going to be the tautomeric form. So here also tautomer will exist, and oxime is going to be the tautomeric form of nitro. So let us move ahead. Here, can you name this particular compound? R C double bond O NH2. What's the functional group here? Amide. Amide, right, students? Here the functional group is amide. Now, will it exhibit tautomerism? Yes, it may. Why? Because this one is X, this one is Y. X doubly bonded Y. This is going to be the alpha carbon having hydrogen. But from this side also, C or N single bond X doubly bonded Y. So from this side also we can do the oscillation of hydrogen, right? Okay. Now the question is, from which side I am going to do the oscillation? From which hydrogen I am going to move? The hydrogen connected to carbon or the hydrogen connected to nitrogen? Students, always remember in tautomer, or in the while writing the tautomeric form, we always move the most, or we always do the oscillation of most acidic hydrogen. Which hydrogen is more acidic? The hydrogen connected to nitrogen or the hydrogen connected to carbon? Obviously the hydrogen connected to nitrogen is relatively more acidic, because this hydrogen is connected to more electronegative element, right? So I am going to do the oscillation from nitrogen side. So it will be like this. See, right, students? Here I will have single bond OH. Here I will have doubly bond NH. I hope you understood this. This particular compound is imine, and this is all, right? So iminol. C double bond NH is imine, and this one is all. So this compound will be referred as iminol, tautomeric form. So for amides also we can draw the tautomeric form, and this is going to be the tautomeric form. The most important concept here was which hydrogen will oscillate. Always that hydrogen will oscillate which is relatively more acidic. Okay, let's move ahead. Here, if we look at this particular group, can I say this is nothing but nitroalkane? Is it fulfilling the criteria of tautomerism? Yes. X doubly bond Y, carbon, alpha carbon having alpha hydrogen, right? Migration of this acidic hydrogen from C to O. What I am going to do, I will simply draw it. CH2 doubly bond NOH, right, students? And here I will have this one remaining as it is. So this is going to be the tautomeric form of this particular compound, right? I hope you understood this one. This is nothing but nitro, and this is acetonitro. Nitro, acetonitro. Let's move to the next one. Will this compound exhibit tautomerism? Let's see. Can I say this one is going to be X and this is going to be Y? Perfect. So this one can be the alpha carbon and this one will also be the alpha carbon. Do we have any alpha hydrogen here? Do we have any alpha hydrogen here? The answer is no. Right? Do we have any alpha hydrogen here? The answer is yes. One alpha hydrogen is here. So can I do the migration of, or can I do the oscillation of this acidic hydrogen from C2O? Student, if this hydrogen will migrate from C2O, I will have double bond on bridgehead carbon. And bridgehead carbon cannot be sp2 hybridized. Right? Bridgehead carbon cannot be planar. So I cannot do the oscillation of this particular hydrogen. So this compound will not exhibit tautomerism. No tautomerism. I hope you understood this particular question also. Let us move ahead. Will this compound exhibit tautomerism? Do we have any alpha carbon here? Okay, let's see. This is going to be the alpha carbon, sp3 hybridized, but do we have any alpha hydrogen here? No alpha H. No alpha H. Right? Okay. This is going to be once again the alpha carbon, but this is sp2 hybridized. So what I will do, if this carbonyl group is in conjugation with double bond, can I say here this double bond is in resonance with this C double bond O? That's why in the first class I had discussed GOC. Then only I started this isomerism. The basic reason was, in this isomerism chapter, mainly in Tautomers, we need lot of concepts of related to GOC, electronic effects, resonance, hyperconjugation, all these things. Okay, so can I say this double bond is in conjugation with C double bond O? Definitely it's there in conjugation. So now students, whenever this C double bond C is in conjugation with C double bond O, you need to check only one thing. Move to the next carbon. I'm going to move to the next carbon and see whether do we have any alpha hydrogen or not. Yes, here also this carbon is sp3 hybrid carbon. So if I am getting a sp2 hybrid carbon, just move to the next sp3 hybrid carbon and check whether it is having alpha hydrogen or not. Here definitely we have alpha hydrogen. Now in this particular case, the movement of alpha hydrogen will occur from this carbon. So I will have the oscillation of this acidic hydrogen from this carbon to oxygen. And what I am going to draw? Student, suppose if this acidic hydrogen will migrate, acidic hydrogen always moves in the form of H plus. So can I say here I will have negative charge, and now this negative charge, here I can have this negative charge. If I draw it in a better way, can I draw it like this? Now can I say this negative charge will be in resonance with this ring, or will be in resonance with this double bond, and here this bond will shift over here, and finally it will shift over here. So if I draw the final resonating structure, can I say I will get it like this, right? Now I have removed this acidic hydrogen, so this acidic hydrogen will get attached here, right student? So this is going to be the tautomeric form of this particular compound. I hope you understood it, right? Now this is going to be the tautomeric form of this particular alpha beta. This one is alpha beta unsaturated carbonyl. So whenever I'm having alpha beta unsaturated carbonyl, then we do the oscillation from the next sp3 hybrid carbon. We do the oscillation of acidic hydrogen from the neighboring sp3 hybrid carbon, and such a tautomerism is referred as space tautomerism, space tautomerism, or para-tautomers. Para-tautomers. Tautomers. Right, student? Let's move to the next case. Will this particular compound exhibit tautomerism? Let's see. Can I say X double bond Y, X double bond Y, X double bond Y? For this X double bond Y, can I say this one carbon as alpha carbon? For this one, can I say this is going to be the alpha carbon having alpha hydrogen, alpha carbon having alpha hydrogen, and for this X doubly bonded Y, can I say alpha carbon having alpha hydrogen? From each alpha carbon, I'm going to remove acidic hydrogen and I'm going to attach it on Y. Then I will have the form like this. Right, student? OH. From this alpha carbon, once again I am going to remove OH. From this alpha carbon, once again I am going to remove. And here, sorry, here I will have one more OH. OH. Right? So this is going to be the tautomeric form of this particular tri-keto group, right? Trion system, it's there, right? And this is going to be the tautomeric form of this particular compound. Now, student, you will find while writing the tautomeric form, in every tautomeric form, the length of or the condition of the reversibility, the length of these two arrows are not the same. You will find everywhere. Right? Why I have drawn it like this? It simply means at equilibrium, both the forms are not having equal concentration. One of the form is dominating over the other one. So now we need to understand at equilibrium which form will dominate. Let us try to understand that. Student, now it's time to discuss the comparison of relative stability of the tautomeric form. At equilibrium, which tautomeric form will dominate? Let's start with keto enol itself. Students, I'm having CH3 H H C double bond OH, right? Keto form. So obviously the tautomeric form of this one is feasible, and that is nothing but enolic form, and I am going to write simply the enolic form. I believe now you easily understand this particular compound will exhibit tautomerism, and this is going to be the tautomeric form of this. Now at equilibrium, which one will dominate? Can you tell me? Okay, how to decide? Student, there are two methods through which we can decide. One is the bond energy method, right? We have studied the bond energy of C double bond O is more than that of C double bond C. This one is having higher bond energy, so obviously the one having higher bond energy is relatively more stable, and the one which is more stable at equilibrium will have the larger amount at equilibrium. So at equilibrium, this one is going to be the major, right? Okay, this is one of the form, one of the conditions through which we can say. But student, always you cannot remember the bond energy of each and every bonds, right? So I am giving you a shortcut. Basically, now we are going to use physical chemistry concept. Let's see. Can I say here, this hydrogen is acidic, right? Alpha carbon containing hydrogen is alpha hydrogen, and alpha hydrogen is relatively more acidic. So in this particular compound, these three hydrogens are going to be the most acidic. Okay. Here, can I say in the enolic form, can I say this hydrogen is going to be more acidic? Let's say it as HB and let's say it as HA. Can you say simply which hydrogen will be more acidic? HB or HA? Students, obviously HB is more acidic. Why? Connected to a highly electronegative element, oxygen. This one is connected to carbon. Can I say it is going to be a strong acid? And can I say it is going to be a weak acid? Now we have studied Le-Chatelier's principle. And what does it say? At equilibrium, a strong acid always moves in the direction of weaker acid. So this particular reaction will always shift in the reverse direction. Reverse direction. So can I say at equilibrium, this weaker acid will have larger amount, right? So can I say at equilibrium, this one will be having larger concentration. So can I say it is going to be major, right? Student, always remember, in case of monocarbonyl compound, what do we mean by monocarbonyl compound? The compound having single C double bond O group, monocarbonyl. So in case of monocarbonyl compounds, keto form always dominates over enol. And if you will compare the relative amount, almost 98 to 99% is there. Hardly 1%. Hardly 1%. Right, student? So I hope you understood why keto dominates over enol. The basic reason is keto is relatively weaker acid. So at equilibrium, the reaction will shift towards weaker acid, from strong acid to weaker acid. So weaker acid will have the larger amount, right? At equilibrium, this one will be having more concentration. It will exist as a major product. This one major, this one minor. I hope you understood this one. Okay, let's discuss few more cases and let's discuss their comparative stability. I'm having C, H, 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 doubly bond NH. Obviously, this one will also exhibit tautomerism, and if I'm going to write the tautomer form, it's nothing but enamine form. It is going to be CH2 doubly bonded NHH, right? This is enamine. Now, which one will be major, imine or enamine? How do we compare? Simply compare the relative acidic strength. Okay, can I say here the acidic hydrogen is this one? And can I say here the acidic hydrogen is going to be this one? The hydrogen connected to nitrogen is relatively more acidic. So can I say this one has a stronger acid? Can I say this one has weaker acid? Weak acid. Reaction always shifts in the direction of strong acid to weak acid. From a strong acid, reaction always shifts in the direction of weaker acid. Strong acid plus strong base always moves in the direction of weak acid plus weak base. So can I say at equilibrium, this is going to be the major and enamine will be minor. Major and minor. Now student, you will say, sir, always what I am saying, this particular keto form means the keto form having the general formula, the tautomers having the general formula, C single bond X double bond Y is only dominating because enolic form is always more acidic. So will always the keto form dominate over enol? No, students. We are having certain cases where the extent of enolization is more as compared to keto. Now we need to discuss those cases itself. Let's start our discussion. Students, already I have told you people, there are certain cases where the extent of enolization is more. So what all factors are responsible for it? The governing factor. First, if in case aromaticity is achieved in the enolic compound, then in that particular case, the extent of enolization will be more, or we can say enol will be the major one. In that particular case, keto is going to be the minor one. Let's discuss that first of all. Aromaticity, the first factor. Aromaticity is achieved. Let's assume like this. I'm having a compound like this. Okay, and here what I am going to draw, this one. Okay, and this one. Okay, let's draw the tautomeric form. Already I have told you people, here we can have space tautomerism, and if I am going to write the tautomeric form of this particular compound, the tautomeric form is going to be like this: 1 pi bond over here, alpha beta. So now this pi bond will shift over here. Already 1 pi bond is already here, and here I will have OH, right? So this is going to be the keto form. This is going to be the enolic form. Now you only tell me, at equilibrium, which particular compound is going to be more stable? Obviously the aromatic compounds. Benzene, highly stable ring, right? So this is going to be the major, and this one will be the minor. So in case if aromaticity is achieved, then in that particular case enol will dominate over keto. One more case. Okay, let's do tautomeric form of this one also. Can I draw the tautomeric form of this particular compound? Definitely yes. Please do it and tell me how many of you were able to do it. Do it ASAP. Okay, alpha carbon, alpha hydrogen. So from here I am going to move this one, and here I will have OH. From here also I can do the oscillation, right? And can I say the tautomeric form of this particular compound is going to be this one? Now here also I will have one OH, and here simply one double bond. I have removed this double bond OH. One double bond, I have removed this C double bond O, C single bond OH. Now at equilibrium, which one will dominate? Obviously the enol. Why? Because enolic compound is aromatic one. Aromatic. So in all such cases where aromaticity is achieved, extent of enolization will be more. The second case, the second factor, intramolecular H bonding. Student, this intramolecular H bonding is achieved in a special case, and mainly it is achieved in case of beta dicarbonyl compounds. Beta dicarbonyl compounds. Let's discuss that. Beta dicarbonyl compounds. Okay, what do we mean by beta dicarbonyl? Let's draw the general formula or general structure. I can have R, C, double bond O. It's better to write alkyl itself, because then only we can see whether it is having acidic hydrogen or not. So CS3, C double bond O, okay, CH2, C double bond O, H. Okay, now let's see whether this compound is beta dicarbonyl compound or no. Or what do we mean by this term beta dicarbonyl? The name itself says dicarbonyl, means two carbonylic groups. Can I say this particular carbon as alpha carbon? So can I say this carbon will be beta for this particular carbonylic carbon? And this carbonylic carbon will be at beta position with respect to the left carbonylic carbon. So basically they are at beta position with respect to each other. Both the carbonylic forms are at beta position with respect to each other. That's why we name this compound as beta dicarbonyl compound. Now one more thing, student. This particular carbon, this is nothing but CH2. So we name it as active methylene group. Active methylene group, and the hydrogen connected to this CH2 group, basically which is sandwiched between two carbonylic carbon, is nothing but the carbon sandwiched between two carbonylic carbon is referred as active methylene carbon, and the hydrogen connected to this active methylene carbon is more acidic. Hydrogen connected to this carbonylic carbon is always more acidic. Why? Simply you check it. What do? You remove one hydrogen. As soon as you remove the acidic hydrogen, you will form the anion. I will have carbon ion. Now compare the stability of this carbon ion. Can I say it is basically stabilized by two strong electron withdrawing group? Right? So can I say this carbon ion is relatively more stable because I am having C double bond O group from left and C double bond O group from right? So the stability of carbon ion is more. Stability of conjugate more means more acidic strength. So in case of beta dicarbonyl compound, always remove acidic hydrogen from active methylene group. Okay. Now, if I remove the acidic hydrogen, now I am simply going to do the tautomerization. Okay. Let's do it on either side. Either I can do on the left side or I can do on the right side. Let me do on the right side itself. So this one will delocalize, and this one already I have removed one acidic hydrogen. So if I am going to write the tautomeric form, can I write it like this? CH3 will remain as it is. Now I will have C doubly bond O, CH doubly bond C, single bond YH. Right, student? Can I say this is going to be the enolic form? Now let's discuss about this enolic form. We'll write it separately and we'll discuss about this. So students, now let's write the structure itself first of all. I'm having CH3, C double bond O, CH doubly bonded C O H H. Right? This was the enolic form. Now we need to check whether intramolecular H bonding is present here or not. Okay. Let's see. Can I say this hydrogen is acidic? Okay. And it is connected to a highly electronegative atom, oxygen. Here I am having lone pair. So can I say here I can have a dipole-dipole interaction, and which type of dipole interaction will it be there? Intramolecular H bonding. Okay. So do we have any chelation here? And if ring formation is there, what's the size of ring formed? 1, 2, 3, 4, 5, 6. So can I say in case of beta dicarbonyl compounds, I'm having 6-member cyclic intramolecular H bonding. 6-member cyclic ring formation due to IMHB, intramolecular hydrogen bonding. Right, student? So because of this intramolecular hydrogen bonding, that too with the formation of a 6-member cyclic ring, obviously here the extent of enolization will be more. One more thing is here. Oxygen is having lone pair, right? What's the hybridization of this oxygen? sp2. Why it's sp2? Because one of the lone pair will participate in resonance. So can I say will have delocalization from this oxygen to carbon, to this carbon, to this carbon, and finally up to this oxygen. So can I say I will have extended conjugation also? Extended conjugation. So because of these two factors, first 6-member cyclic ring formation because of the intramolecular hydrogen bonding, and second because of extended conjugation, in case of beta dicarbonyl compound, enolic form dominates over keto form. So enolic form will be the major form. Major, keto is going to be keto will be minor. Right, students? I hope you understood this particular question also. So here basically I will have this one as the enol as the major and keto as the minor. Major, minor. Right? Okay. Students, now let's discuss some of the questions in order to brush up your concepts. The first question, I am having a alpha dicarbonyl compound. Alpha dicarbonyl compound. And if alpha dicarbonyl compound, let's draw all the possible tautomeric form of this particular compound. The first one, I can draw it like this. OH, double bond O. The second one, OH, double bond O. Now, which one will be more stable? Let's see. Student, can I say in the second one, I can have intramolecular hydrogen bonding? Let's see. O connected bonded to H. This hydrogen is acidic. This obviously this oxygen is having lone pair electron rich species. So I can have IMHB 1, 2, 3, 4, 5, a 5-member cyclic ring formation, and because of that, because of intramolecular hydrogen bonding, this particular compound will be relatively more stable. So 5-member cyclic ring formation, or we can say chelation, because of IMHB, intramolecular hydrogen bonding. Let's check the possibility whether we can have IMHB here or not. You will say, so here also we can have hydrogen bonding, right? This hydrogen is acidic and I'm having oxygen. But student, basically this oxygen lone pair is localized. And if I talk about the lone pair present on this oxygen, it's used in resonance. Because of delocalization, this oxygen will have del positive charge appearing on it. Now, if it is having a del positive charge, how it can participate in dipole-dipole interaction? Already this hydrogen is having del positive. How it can form bond with this hydrogen, right? The like charges repel each other. So we cannot have no IMHB. Now, if I compare the relative stability of 1 and 3, this is going to be 2. Can I say 1 will be relatively more stable? Why? Because the bond energy of C double bond O is higher as compared to the bond energy of C double bond C. So if I write the relative stability, can I say second is more stable? The region is intramolecular hydrogen bonding, right? Then I will have the first one, and then I will have the third one. Right, student? Let's move ahead. Compare the extent of enolization in the following cases. Basically, if I look at all these compounds are the cases of beta dicarbonyl compounds, right? And in beta dicarbonyl compounds, everywhere extent of enolization is going to be more. Enolic form will dominate over the keto one. Okay. Here I am having one hydrogen, one alkyl group. If I do the tautomerization, I will have the structure formed like this, right? OH, right? Here I will have OH, remove this bond, and here I will have OH. Now students, whenever you compare the extent of enolization, always check the relative strength of acidic hydrogen. Which hydrogen is more acidic? Can I say here, no doubt, all the hydrogens are basically the hydrogens of active methylene group. But here, with addition to this active methylene group, I am having one more NO2 group. And this NO2 group acts as minus I, and the strong minus I effect. Because of that, the stability of carbon ion or the conjugate will be higher. Higher the stability of conjugate, better is the acidic strength, right students? So can I say in this particular case, the hydrogen connected here will be more acidic. And if nothing is mentioned, always if you need to compare the relative extent of enolization, always check the acidic strength. Higher the acidic strength, higher will be the extent of enolization. This one, third, right student? Maximum acidic. Here, can I say, no doubt I am having C double bond O group and CH3 group from one side. C double bond O group, and both these C double bond O group will stabilize the carbon and form from here. But if I compare the relative stability, which carbon ion will be more stable? Can I say the first one? Why? Because here I am having C double bond O CH3 and C double bond O H. Aldehyde, a better minus I as compared to ketone, right? So the carbon ion connected to a aldehyde will be more stable as compared to the carbon ion connected to a keto group. So the relative stability order will be like this: third, then 1, then 2. Student, basically Tautomerism is a catalytic driven process. Either it is catalyzed by acid or it is catalyzed by a base. If it is a base catalyzed process, always check the stability of carbon ion. If it is a base catalyzed process, always check the stability of carbon ion. If it is a acid catalyzed process, if the tautomerism process is occurring in acidic medium, then always check the stability of carbocation. In case of acid catalyzed tautomerism, only you need to check alpha hydrogen. More is the number of alpha hydrogen, better is the extent of enolization. In case of base catalyzed tautomerism process, always check whether electron withdrawing groups are present or not. With the presence of electron withdrawing group, the extent of enolization is going to be more. Now let's discuss the effect of solvent in tautomerism. If I talk about the types of solvent, we are having two types of solvent: polar solvent and non-polar solvent. Polar and non-polar. Non-polar. If I talk about polar solvent, it's further categorized as polar protic, polar aprotic, right? What do we mean by polar protic solvent? The solvent whose dipole moment is non-zero, at the same time it is having one acidic hydrogen. It is having a tendency to release H+. Such solvents are polar protic solvent. The best example is water, alcohol. These are basically polar protic solvent. If I talk about polar aprotic solvent, here also the dipole moment is non-zero. In case of polar solvent, the dipole moment is always non-zero, not equals to 0. It has to be greater than 0. The second thing, if I talk about this aprotic, the solvent which does not have acidic hydrogen, which does not have a tendency to release proton, which does not have a tendency to release H+, such solvents are polar aprotic solvents. The best example is acetone, DMSO, like that. Right? If I talk about non-polar solvents, generally the organic solvents are, most of the organic solvents are non-polar, like N-hexane, CCl4, right? Now, so this was all about solvent. Now, what's the impact of solvent in tautomerism? Students, we have studied the driving force for this keto-enol tautomerization is intermolecular hydrogen bonding, right? Generally, keto forms enol mainly because as soon as it forms enol, then this keto and enol will get stabilized by intermolecular hydrogen bonding. But if I am taking a polar protic solvent, let's assume I am taking a keto compound CH3, C double bond OH, and I am taking it in water. This aldehyde is taken in a polar protic solvent. Now, is there a need or will this compound exhibit tautomerism? No doubt it will exhibit tautomerism, but the extent of tautomerism or the extent of enolization will be less. Why? Because this keto form will form intermolecular hydrogen bonding with water itself. Keto will form IMHB with the solvent itself. So students, in polar protic solvent, the extent of enolization is going to be very, very less. The main reason is simply the keto form simply forms intermolecular hydrogen bonding with the solvent itself, so it does not need enol for its further stability. Now, what will be the impact in case of non-polar solvent? Now, in non-polar solvent, the keto form can't form intermolecular hydrogen bonding. So, in that particular case, it needs enolic form, and with the formation of enolic form, we will have intermolecular hydrogen bonding, and the stability of keto will further get enhanced. So, in non-polar solvent, enolic content increases, right? In polar solvent, the extent of enolization is less. I hope you understood it. Now let's discuss the last subtopic of this tautomerism, and that's nothing but deuterium exchange. Students, sometimes you will see reactions like this. I'm having a keto group or any aldehydic or keto compounds, and you will find basically it is treated with OD minus slash DTO. So I'm treating this carbonylic carbon in an alkaline medium, and here I'm taking the isotopic form of hydrogen. Basically, I'm taking deuterium. What will be the impact? Simply, you need to do only one thing. Replace all the acidic hydrogen. Replace all the acidic hydrogen with D. How many acidic hydrogens are there? 2 hydrogen from this side and 2 hydrogen from left side. So all these 4 acidic hydrogen will simply get replaced by deuterium, and I will have a formation like this: D, 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 and D. Right, students? Let's move to the next question. Here also, if this particular compound is treated with a base OD minus in the presence of D2O, you need to simply remove the acidic hydrogen. Now you will say, so this hydrogen is only the acidic hydrogen? Not at all. See, first I will form the carbon ion, and now I will check at which carbon. Once again, this carbon ion is getting delocalized. I will do resonance. So here also I am getting the negative charge, right, students? Now, can I do resonance like this also? So can I say at this carbon also I will have negative charge, right? So can I say I will have the formation of carbon ion at this carbon and these 2 carbons. So all the hydrogens connected to these carbons are going to be the acidic one, right? So in such process, you need to replace all the hydrogens connected to these 3 circled carbon. So what you need to do? You need to simply put 1D over here, right? And 2D over here. So how many hydrogens are replaced here also? 4 hydrogens are replaced by deuterium. So student, this was all about a brief discussion of tautomerism. I hope you understood this particular tautomerism. Now it's time to discuss stereoisomers. Students, now let's start our discussion on one of the most important subtopic of this chapter, isomerism, and that is stereoisomers. How do we define it? It's nothing but the compounds having the same molecular formula, same structural formula, but different arrangement or orientation of atoms or groups in 3-dimensional space. The compounds are related as stereoisomers of each other. Basically, it's of 2 types, configurational and conformational. If I talk about this configurational isomers, the compounds having the same molecular formula, but here they differ in arrangement of atoms on or groups. Differ in arrangement of atoms or groups in three-dimensional space. Then such compounds are basically configurational isomers. Configurational isomers mainly arises because of difference in arrangement. Now let's talk about this conformational isomers. Such isomers basically arises because of difference in orientation. They differ in orientation of atoms or groups in three-dimensional space. What do we mean by orientation? What do we mean by difference in orientation? Student, around CC bond or around any sigma covalent bond, we are having free rotation. Let us suppose one hand is representing one carbon and this palm is also representing one carbon. These two carbons are connected via a sigma covalent bond. Around sigma covalent bond, I am having free rotation. So now what I am doing, I am keeping this carbon fixed and now I am rotating it. As I am rotating it, I am getting different orientations. And these different orientations are nothing but conformers of each other. We will discuss about that in today's lecture itself. Now, let's first of all try to understand this configurational and conformational isomers with one example. Okay, what do we mean by difference in arrangement? What do we mean by difference in orientation? Let's try to understand it. Okay, I'm going to take one example, C. On this carbon, three groups are connected. Let's assume A, B, D. Here also, the groups connected are A, B, D. Now, these two carbons C1 and C2, they are connected via sigma covalent bond. Around sigma covalent bond, there is free rotation. Okay. So what I am doing, I am keeping this one fixed and now I am rotating this one. Okay. If I rotate it by 180 degree, what I will get? A, B, D, right? Now here I will have A, I will have D, and I will have B. These two compounds basically differ in orientation. 1 and 2 differ in orientation. So how these two will be related? They are the conformational isomers of each other. If I rotate it back by 180 degree, I am going to get back my original structure, right? If I rotate it further by 180 degree, I will get back my original structure. Now, let's do one more case. C. It was A, B, D. Now, D, B, and let us suppose it is A. Now, you try to rotate it. This is compound 3. By rotation, can you come back to the original first one? No, I don't think so. You rotate it. If I rotate it like this, then this D will come here. This B will come here. So by rotation, I cannot go back to my original structure. So basically compound 1 and compound 3 are differing in arrangement of groups. They 1 and 3 differ in arrangement, right? So how these 1 and 3 will be related with each other? They are nothing but configurational isomers of each other. I hope you understood what do we mean by difference in arrangement, and what do we mean by difference in orientation. Let's move ahead. Student, if I talk about this configurational isomers, we are having mainly two types of configurational isomers. The first one is geometrical isomers. Geometrical isomers. And the next one is optical isomers. Optical isomers. Right? We'll discuss each of these isomers. Students, if I talk about the sequence or the order in which we are going to do this stereoisomers, first we will do geometrical isomers, that's the part of configurational isomers. Then we'll move to conformational isomers, and at the end we are going to do this optical isomers if the time permits, or we will do this optical isomers in the next lecture, in the lecture of reaction mechanism itself. We have to do basic strength there also, and there only we will do optical isomers if today we are not able to complete it, because optical isomers is really a bit lengthy subtopic. We cannot simply rush and we cannot simply complete it in 20 minutes or 30 minutes. It will take at least 1.5 hours. So what we will do, we'll simply, first of all, we'll complete geometrical, then we'll complete conformational, and then at the end we will do this optical, either today or in the next lecture. Students, let's start our discussion on geometrical isomers. Is it a type of configurational isomers? Yes. Is it a type of stereoisomers? Yes. Stereoisomers two type, configurational, conformational. Configurational again two type, geometrical and optical. Now it's time to first of all understand the basic definition of geometrical isomers. Let me write that and then I will explain. Compounds having same molecular formula, same structural formula. This one is also very important. Structural formula. If the structural formula is not the same, then there will be a structural isomers. A structural formula but different arrangement of atoms or groups in a three-dimensional space which arises purely because of restricted rotation. Restricted rotation. Okay. So we have written the definition part. Compound having the same molecular formula, same structural formula. If the structural formula is not the same but the molecular formula is same, then there will be a structural isomers, not a stereoisomers. So the compound having the same molecular formula, same structural formula, but different arrangement of atoms or groups in a three-dimensional space across a restricted center. Basically, such stereoisomers differ in geometry, or such stereoisomers differ in arrangement of atoms or groups across a restricted center, right? So for geometrical isomers, restriction in rotation is always a necessary criteria. Now, what do we mean by this restriction in rotation? Student, if I am having a sigma bond, can I say I will have a free rotation? Carbon, free rotation. But if one more bond is there, then it will be very tough for me to move my hand. If I will move my hand, what will happen? The bond will break. So across a double bond, we always find restriction in rotation. Can you tell me one more case where we find restriction in rotation? Student, we find restriction in rotation in case of ring structure also, right? So geometrical isomers is mainly feasible when I am having a double bond or I am having a ring structure. One or two more cases are there where we can have restriction in rotation, and that we will discuss later on, but in the same class, in today's class itself. Let's move ahead. Moving ahead, students, now it's time to discuss what are the different conditions for a molecule to exhibit geometrical isomers. The first, restriction in rotation. Let's talk about the conditions for a molecule to exhibit geometrical isomers. Condition number 1, restriction in rotation. Restriction in rotation. And where do we find this restriction in rotation? Across a double bond or a triple bond, mainly across a double bond or a ring structure. Ring structure. Second one, the most important one, the restricted atoms should have different groups connected to them. The restricted atoms should have different groups connected to them. Let's write that. Restricted atoms should have different groups connected to them. Let us try to understand it. First, can I have restriction in rotation here? Yes, there is restriction in rotation. Can I have restriction in rotation here? Yes. Can I have restriction in rotation here? Yes. Can I have restriction in rotation here? Definitely we can have. Can I have restriction in rotation here? In all such cases we can have restriction in rotation. So all these 1, 2, 3, 4, 5, all these 5 examples are fulfilling the criteria number 1. Now coming to criteria number 2, restricted atoms or restricted centers. So can I say these 2 carbons are basically the restricted centers. Across these 2 carbon, the rotation is always restricted. There is always restriction in rotation. Now across these 2 restricted centers, or if we look at this one, now how many groups can be attached to this carbon? Only 2 more groups. The 2 groups connected should be different. On one restricted centers, the 2 groups connected should be different. Again, on this restricted centers also, the groups connected should not be same. It can be AB, it can be CD, it can be EF, GH, but it cannot be AA. If it is AA, it won't show. Are you getting my point? If it is AA, it will not show. Okay. Here, can I have restriction in rotation here? Definitely we are having restriction in rotation. I can have, now coming to the groups, I can have AB groups here. Now coming here, let me put one hydrogen here. Is it fulfilling the criteria or is it fulfilling the conditions for a molecule to show GI? Let's talk. Let's first of all see whether there is restriction in rotation or not. Yes, there is restriction in rotation. Across C and N, the rotation is restricted, right? Now, is the restricted centers having different groups connected? Yes, this carbon is having AB group connected. Is this also the restricted center? Is it having different groups connected? Yes, student, it is also having different groups connected to it. How? You will say, sir, only hydrogen is there. Student, one lone pair is also there. So is it fulfilling the criteria? 100%. Now, Oxygen, oxygen. Is there restriction in rotation? Definitely there is restriction in rotation. Will this compound show or exhibit GI? Let's talk. This oxygen is having two lone pairs. This oxygen is also having two lone pairs. Now you only tell me, will it exhibit GI? No doubt there is restriction in rotation here, right? But both the restricted centers are having the same groups connected to them, right, students? So will it exhibit GI? The answer is no, not at all. Okay, let's talk about this one. I can have one H here. I can have one H here. Will it exhibit GI? Tell me. I'm giving you 10 seconds. Restriction in rotation, yes. Condition number 1 fulfilled. Let's talk about condition number 2. Lone pair. Lone pair. AB groups. AB groups. Double bond. AB groups on restricted centers. Definitely will show GI. Lone pair. Hydrogen. AB group. AB group. Restriction in rotation will exhibit GI. Now let's students, I'm giving you a cyclic compound, a 6-member cyclic ring. Okay, on carbon 1, I'm having two groups connected. One is A, one is hydrogen. On carbon number 3, I'm having two groups connected. One is group B and the other one is hydrogen. Now I am simply asking you, tell me whether this compound will exhibit GI or not. Whether this compound will show GI or not. Students, I have told you earlier, for a molecule to exhibit GI, only two conditions are primarily important. Although some few more conditions are also there, but two conditions are primarily important. First, restriction in rotation, and second, restricted centers should have different groups connected to them. Now in a ring structure, all the carbons or all the centers are restricted centers. Suppose I am having a 5-member cyclic ring. So all these 5 carbons, across all these 5 carbons, we can have, across all these 5 bonds, we can have restriction in rotation. Across 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 1. Across all these bonds, we will have restriction in rotation. So yes, restriction in rotation criteria is fulfilled. Now, across any two restricted center, either it should be across 1, 2, 1, 3, 1, 4, I should have different groups connected to them on two carbons. On carbon 1, I am having different groups connected to them. On carbon 3, I am having different groups connected to them. So will it show GI? 100%. Tell me. CH3, CH3, will it show GI? There is restriction in rotation on all the carbons. Now I will focus on carbon 1 and carbon 2. Restriction in rotation. Carbon 1 having two different groups connected to them, one methyl, one hydrogen. Carbon 2 having two groups connected to them, one methyl, one hydrogen. One methyl, one hydrogen on carbon 1, one methyl, one hydrogen on carbon 2. Restriction in rotation, restricted centers having different groups connected to them. One restricted center is this one, other is this one. It will definitely show GI. Will it show GI? Tell me. Will it show GI? Will it show GI? Student, it will also show GI. How? One methyl group, one hydrogen. One methyl group, one hydrogen. These two are also the restricted centers, right? And across the restricted centers, I am having different groups connected to them. Now you can say, sir, here I am having AA group. We have to check only two carbons. For a molecule, for a ring structure to show GI, two conditions have, or only one condition has to be there, right? That condition is on two carbons, I should have two different groups connected to them. Or on the restricted centers, I should have different groups connected to them, right? So this one will also show GI. I hope you understood this one. Now let's move ahead. Now it's time to discuss the different cases of geometrical isomers. The first case which we are going to discuss, that is geometrical isomers in C double bond C. Is the rotation hindered in C double bond C? 100%. Whenever I am having a double bond, the rotation is always restricted or hindered. Okay. Now, I'm having C double bond C. So rotation is hindered. Now one group connected here is methyl, one group connected is hydrogen. One group connected is hydrogen, other group connected is methyl. Now, if I look at this particular compound, will it exhibit GI? The answer is 100% yes. Now you have understood the criteria for GI. So you can easily say yes, this compound will show GI. Now, if GI is feasible, we will have two different arrangement, right? And these two arrangements are like this. CH3H, CH3H. So these are the two possible arrangement of this particular compound in three-dimensional space. Now, students, if these two are the arrangements, we will certainly name these two arrangements. Now we'll name these two compounds of these two isomers as cis-trans isomers. So across C double bond C, mainly we define cis-trans geometrical isomers. Now, which one will be cis and which one is going to be trans? Tell me. If similar groups are on the same side, if two similar groups are on the same side, then it is cis. If two similar groups are on the opposite side, then it is trans. I hope you understood this one. If two similar groups on the same side, cis. If two similar groups on the opposite side, it is trans. Anti. Two similar groups on the opposite side, two similar groups on the same side. Now, here, if the length between these two similar groups is L1, will the length between these two similar groups be L1 only? No. Here the length will differ. It will be L2 and L1 will not be L2. Students, now it's also one of the very important criteria for a molecule to show GI. If a molecule is exhibiting GI or if a compound is showing GI, then the two different isomeric forms of that compounds, or we can say in the two different isomeric forms of the compounds, the distance between the two similar groups should not be same. The distance between the two similar groups should not be the same. I hope you understood it. At the same time, I believe that you understood what do we mean by cis-trans isomers. Cis, two similar groups on the same side, trans, two similar groups on the opposite side. Let's move ahead. Students, moving ahead, the next type of geometrical isomers which we have on the screen is oximes, right? Geometrical isomerism across C double bond NOH. This particular group is referred as oxime. Now let's talk about this oxime. I can have a structure like this, R, H, lone pair, OH, right? I can have a structure like this also, R, C, R dash, double bond N, OH, lone pair, right? Student, this particular compound, this oxime is referred as aldo oxime. How it is aldo oxime? Because here aldo oxime and this one is R and R dash. So keto oxime. Keto oxime. It's simply formed by the reaction between aldehydes and hydroxylamine. Here, this particular compounds or such compounds are formed by the reaction between ketone and hydroxylamine. Okay. Now let's first of all talk about geometrical isomers in aldo oxime. Okay. Geometrical isomers in aldo oxime. I am having C double bond N, R, H, OH, lone pair. Now here, instead of defining cis-trans, we have a different name and the name is syn-anti. Now which one will be syn and which one is anti? We need to discuss. Okay, I will have one more form, R H O H lone pair. Student, if the two groups across the restricted center C and N, these are the two groups we need to focus. If H and OH are on the same side, the compound or the aldoxime is referred as syn-aldoxime. Syn-aldoxime. If H and OH are on the opposite side, then we say it as anti. If H and OH anti position with respect to each other, opposite side, such a compounds are referred as antiform or anti-aldoxime. Right? So I hope you understood geometrical isomers in aldoxime. Here we define syn anti. HOH same side syn, HOH opposite side anti. Now you may say, sir, can we define geometrical isomers in ketoxime also? Yes, we can define, because it is fulfilling the criteria. I'm having R and R dash, two alkyl groups different across this restricted center carbon, and here also I'm having two different groups. But now you can say, sir, here there is no H. No doubt I am having OH on the other restricted center, but here there is no hydrogen. So here, students, so with respect to this R, OH is on the same side. So with respect to R, this OH is syn. With respect to this R dash, this OH is anti. So if, let us take one example. I am having C double bond N, OH, lone pair, methyl and ethyl, C2H5. So with respect to methyl, the compound is syn. So can I say syn methyl ketoxime? With respect to ethyl, this OH is anti. So can I say it as anti-ethyl ketoxime? I hope you understood geometrical isomers in aldoxime as well as ketoxime. Aldoximes, HOH same side, then we say it as syn. HOH on the opposite side, it is anti. In case of ketoximes, we check one alkyl group, we focus on one alkyl group, and then we see whether this OH is on the same side or opposite side. If OH is on the same side of that particular alkyl group, then it is syn with respect to that alkyl group. I hope you understood this GI in C double bond N OH. Let's move ahead. Now it's time to discuss geometrical isomers across N double bond N. Such compounds are referred as azo compounds. Azo compounds. Okay, I'm having N double bond N. Now one lone pair, one alkyl group, one lone pair, one alkyl group. Will it exhibit GI? 100% it will exhibit GI. And if it is exhibiting GI, obviously it will have one more form. Let's write that form also. I am going to do the different arrangement. So now here the lone pair here, alkyl here, alkyl here. Now in case of azo compounds, we define geometrical isomers, or we define syn anti with respect to lone pair. If the lone pairs are on the same side, lone pairs on same side, then it is syn. If the lone pairs are on the opposite side, then it is anti, students. I hope you understood what do we mean by syn or anti, or how do we define syn anti forms in case of azo compounds. If lone pairs are on the same side, syn, lone pairs on the opposite side, anti. Let's move ahead. Students, now it's time to discuss geometrical isomers in a ring structure. Right? Let's draw a 6-member cyclic ring. I'm having a 6-member cyclic ring. Okay. So on every carbon there is, on every bond or every carbon there is restriction in rotation. Criteria number 2, the restricted centers should have different groups connected to them. I'm putting one molecule methyl and one methyl here. Now, will it show GI? 100% it will exhibit GI. Why? Because one group is methyl, other one hydrogen. One group is methyl, other one hydrogen. Restriction in rotation and restricted centers having different groups connected to them. Now, students, here also in this compound also, the restriction in rotation is across carbon-carbon. And whenever we have restriction in rotation across carbon-carbon bond, we mainly define cis-trans isomers. So here also, if we define cis, we can simply say similar groups on the same side. But now here, we represent it in other way. We represent it like this. Methyl, methyl. Now you will say, sir, what is this triangle representing? It's referred as wedge. It's nothing but wedge. What do you mean by the term wedge? Means it is out of the plane. If I am the plane and then this pen is representing out of the plane, it's going out of the plane. And one more representation is there, and that is like this. What is this? It is referred as dash. This one was wedge, this one is dash. What is dash representing? It's basically representing the group is going into the plane, negative z axis. This one is positive z axis. This one towards you, this one wedge towards you, dash towards me. I hope you understood what do we mean by wedge and dash. Now, two methyl groups on the same side. It will be cis. Two methyl groups on wedge, cis. One methyl on wedge, one methyl on dash, trans. Let me draw that also. I'm having one methyl group here and one methyl group here, like this. Then it will be referred as trans configuration. I hope you understood what do we mean by cis-trans in a ring structure. Two similar groups on wedge, cis, two similar groups on wedge dash, then it is trans. Antipositions. Now here hydrogen will be on dash and here this hydrogen will be on the wedge. This particular configuration is trans and the upper one was cis. So this is how we define GI in a ring structure, and this is how we define cis-trans isomers in a ring structure. Two similar groups on wedge, cis, one wedge, one dash, similar groups, trans. Let's move ahead. Now, we have defined geometrical isomers in case of cycloalkanes. It's time to define geometrical isomers in case of cycloalkane. Student, up to 7-member ring or up to 7-member cyclic ring, in case of cycloalkene, GI is not feasible. No doubt we have restriction in rotation, even though we can have different groups connected to them also, but still GI is not feasible up to 7-member ring. Geometrical isomers is only feasible from 8-member ring onwards in case of cycloalkene. Okay, let's see it. In case of now let's look at this particular example. I'm having cyclooctene. Okay, will it show GI? Let's first of all check the ring size. Containing 8 carbons. So in cycloalkane, if the number of carbon atom is greater than or equal to 8, then GI is feasible. Now, second case. If GI is feasible, then which one is cis and which one is trans? How to decide? Student, I'm giving you a simple trick. In case of cycloalkane, if the two vertex containing the double bond or if the two carbon containing the double bonds, if their vertex are in the same direction, are pointing in the same direction, then it is cis. If their vertex points in the opposite direction, the two carbon containing double bonds, and if their vertex point in the opposite direction, then it is trans. Let's have a look in case of 10-member cyclic ring. Is GI feasible? 100%. Now, Let's focus on these two carbons. Their vertex are pointing in the same direction. Whereas if we look at this particular configuration here, the vertex is pointing in the opposite direction. One upward, one downward. Here, one downward, one upward. Right? So these configurations are trans. If the vertex point in the same direction like this one, it is going to be cis. If I form a double bond here and if I put one hydrogen here, both the hydrogen are exactly at anti position, then it is a trans one. So GI in cycloalkene is feasible, but from 8-member carbon ring onwards. I hope you understood this particular case also. Let's move ahead, bacho. Students, now let's discuss the third condition of geometrical isomers. And what is the third condition? Condition is the groups connected to the restricted center or all the 4 groups connected to the restricted carbons should lie in the same plane. In order to understand this condition, let's study the case of cumulenes. Whether GI is visible in cumulenes or not, let's see. First of all, can you tell me what do we mean by cumulene system? Cumulene system can be simply written as continuous C double bond C system. Such a system is referred as cumulenes, or we say it as alene system. Okay, now let's first of all discuss the case of cumulenes with even number of pi bonds. What do we mean by cumulene? By the term cumulene with even number of pi bonds? Such a system, 1 pi bond, 2 pi bond. Cumulene with odd number of pi bonds. Such a system is basically referred as cumulene with odd number of pi bonds, even number of pi bonds. Now, the groups connected here are AB. We need to check whether all these 4 groups are lying in the same plane or not. Okay. Can you tell me the hybridization of each carbon here? Can I say it's sp2 hybridized? It is going to be sp hybridized and this one is sp2 hybridized. Now since it's sp2 hybridized, can I say this carbon A and B will lie in the same plane? Let's assume it is lying in xy plane. If it is sp2 hybridized, the orbitals used in hybridization will be s, px and py. So can I say it will have a pure pz orbital? Okay. Now let's move to carbon number 2. What is the hybridization? S and p. So one s orbital and one p orbital. So can I say it will have 2 pure p orbital responsible for the formation of pi bonds. Now between carbon 1 and carbon 2 there is a pi bond. Carbon 1 is having a pz orbital, so can I say the pi bond formed between carbon 1 and carbon 2 is basically formed by the overlap of pz. Right? Now there is also a pi bond formed between carbon 2 and carbon 3, and carbon 2 is having one pure p orbital still left. So can I say the pi bond formed between carbon 2 and carbon 3 will be formed by the overlap of py and py. Okay, students? Okay, so now here this carbon 3 is having a pure py orbital and the hybridization is sp2. So can I say which all orbitals are used in bond formation? The orbitals which will be used in bond formation will be s, px and pz. So can I say this carbon 3 is basically lying in xz plane. The groups connected to carbon 3 is lying in the xz plane. The groups connected to carbon 1 is lying in the xy plane. The groups connected to restricted center are not coplanar. So student, always keep it in mind. Cumulene with even number of pi bonds will never exhibit GI. Why? Because the groups connected here are not coplanar, and it's also one of the mandatory criteria for a molecule to show GI. I hope you understood condition number 3. Now let's take cumulene with odd number of pi bonds. Here, students, it's odd. 1 pi bond, 2 pi bond, 3 pi bond. Let's once again discuss the hybridization of each carbon. sp2, sp, sp, sp2. Right, students? Okay. If it is sp2 hybridized, can I say it will have a pure p orbital, and that p orbital is going to be py? Okay. Let's assume it is py. So can I say now this carbon A and B, all these groups are lying in the xz plane. I have assumed this py bond, py orbital is there. This pure p orbital is py orbital. Now there is a pi bond formed between carbon 1 and carbon 2. Carbon 1 is having a pure py orbital, so the pi bond formed between carbon 1 and carbon 2 is basically formed by the overlap of py py. So carbon 2 will also have a pure p orbital, but the hybridization of carbon 2 is sp. So can I say it is also having one pure pz orbital? Now there is a pi bond formed between carbon 2 and carbon 3, and carbon 2 is having a pure pz orbital still left. So the pi bond formed between carbon 2 and carbon 3 is basically formed by the overlap of pz orbital. Talking about carbon 3, it's also having a pure py orbital still left, right? Because the hybridization is sp. So two pure p orbitals are there, right? The bond, there is also a pi bond formed between carbon 3 and carbon 4. Right, students? So can I say the pi bond formed between carbon 3 or carbon 4, this pi bond is basically formed by the overlap of this py and py, because pz already used. Now this is py and this is also py. Okay, now carbon 4 is having a pure p orbital py, which is forming the pi bond, and the hybridization is sp2. So which all orbitals are used in bond formation? Can I say it is s, px and pz? So can I say this restricted center is also lying in xz plane? Now the groups AB here and the groups AB here, they are lying in the same plane. They are coplanar. It is fulfilling the criteria. So cumulenes with odd number of pi bonds will exhibit geometrical isomers. I hope you understood it. Cumulene with even number of pi bonds will not show GI. Cumulene with odd number of pi bonds will always exhibit GI. Let's move ahead. Now, let's talk about the case of spirenes. What do we mean by spirene? Such a ring or system are referred as two rings connected at a single point. Such a system is referred as spirene system. Okay. You simply treat one ring equals to one double bond. One ring equals to one double bond. How many rings here? Two rings. So basically it is cumulene with even number of pi bonds. Cumulene with even number of pi bonds will never ever show GI. So spirene with even number of rings will not show GI. Whereas the spirene with odd number of rings, one double bond, one double bond, one double bond, AB, they will be coplanar, fulfilling the criteria, the third criteria of GI, restriction in rotation. Restricted atoms should lie in the same plane, and the groups connected to this restricted center should be different. All the three criteria will definitely show GI. So spirenes with odd number of rings will show GI. Spirenes with even number of rings will not exhibit GI. I hope you understood it. Let's move ahead. Now, students, it's time to practice few questions and to check which all compounds will exhibit GI. I am giving you 1 minute for these two questions, then we'll do the next one. Let's do it. Shall we start now? Okay. Students, let's have a look at this particular compound. I'm having restriction in rotation criteria number 1 fulfilled. It's not a cumulenes system, so we should not check whether the groups are coplanar or not. Here the groups will obviously be coplanar. Okay, now we need to check whether the restricted centers are having different groups connected to them or not. Yes, A, B. So on one restricted center, it's fulfilling the criteria. On the next restricted center, here, one of the group is OH, A group, and one of the group is lone pair. So AB group, restriction in rotation will exhibit GI. This one, cumulene system, continuous double bond system. 1 pi bond, 2 pi bond, 3 pi bond. Cumulenes with odd number of pi bonds, fulfilling the criteria number 3. Is it fulfilling the other criteria? AB group, restriction in rotation, 100%. So all the 3 criteria tick marked. First, restriction in rotation, restricted atoms having different groups connected to them, and these groups are coplanar, so will exhibit GI. I hope you understood this particular question also. Let's move ahead, student. This one, will this particular compound exhibit GI or not? Can you tell me? Okay, let's see. I'm having restriction in rotation throughout the ring, but here in the ring only one carbon is there where I'm having AB group, right? Also here also I'm having restriction in rotation. Now these two are the restricted centers, right, students? On this restricted centers I'm having AB groups connected, and now let's check here. Let's move in this manner. Okay, 2 degree carbon, 2 degree carbon. Here I'm having a 3 degree carbon. So can I say A, one group is A, the other group is going to be B? So yes, geometrical isomerism is possible through this restricted center. Ring in double bond with this carbon. GI is feasible. This one. Pyrene in continuation with double bond. Pyrene double bond. So can I say basically I have converted this compound with cumulene with even number of pi bonds, will not show GI. Okay, this one, let's see. Ring, one double bond. The third question, once again I'm having a cyclic ring. Here I'm having a AB groups connected, right? Okay, a 3-member cyclic ring. Okay, so it can be treated as a pi bond. So I'm having a continuous double bond system. Cumulenes with even number of pi bonds will not show GI, right, students? Let's move ahead. Students, moving to the next question which we have on the screen, and the question is, I'm having this ring, okay, pyrene, so it's basically cumulenes with 1 double bond, 2 double bond, and 3 double bond. Cumulene with odd number of pi bonds, having AB group, will it exhibit GI? Definitely. Okay, next one, cycloalkene, greater than 8-member ring, will exhibit GI, and basically it's nothing but the transform, so will show GI. Moving ahead. Now whether this one will show GI or not. Student, I was telling you about that in the beginning itself. I had told you restriction in rotation is not only in case of cyclic compounds or in case of pi bonds. Even if there is lot of steric crowding, then also the rotation is hindered and the region is steric crowding. Now here I am having 2 phenyl groups connected, biphenyl rings, right, students? Now, and the bulky groups are there at the ortho position. Now, because of the steric crowding at ortho positions, these 2 groups, first it leaves the plane because of the steric crowding, and rotation is also hindered, so will not show GI. Right? Let's talk about this one. It's a triphenyl system. These 2 groups are not showing GI mainly because the rings are perpendicular. And why the rings are perpendicular? Because of steric crowding. In order to avoid the steric repulsion, the 2 rings becomes perpendicular to each other. Talking about the three triphenyl system, 3 rings connected. At ortho positions, once again I am having a blocking, right? Now, I'm having nitro group here, Br, nitro, Br, Br, nitro, like that. Okay, let's try to analyze this situation. Obviously, these two rings will be perpendicular, and 1, 2, 3, ring 1 and ring 2 will be perpendicular. Again, ring 2 and ring 3 will be perpendicular. So, can I say ring 1 and ring 3 is going to be coplanar? Criteria number 2. The restriction is also hindered. Sorry, the rotation is also hindered. There is restriction in rotation. And why there is restriction in rotation? Because of steric crowding. Steric crowding. Right? We cannot rotate these two phenyl system. If I will rotate these four groups will start colliding with each other. The bond will break. So the rotation is hindered or restricted. So ring 1 and ring 3, they are coplanar, fulfilling the criteria of coplanarity. Rotation is hindered, so this one will exhibit GI. So in triphenyl system, we are having a possibility of restriction in rotation, or we are having a possibility of geometrical isomers. Why? Mainly because of steric crowding. I hope you understood this particular question. Let's move ahead. Students, moving ahead, now it's time to discuss EZ nomenclature system in geometrical isomers. When do we assign this EZ nomenclature? We assign this EZ nomenclature when all the four groups connected are different, like this. I'm having C double bond C, so there is restriction in rotation, right student? There is restriction in rotation. But you will see here, the groups connected here are AB and the groups connected here are DE. So all the four groups connected to restricted center are different. Now, in case of C double bond C, we were assigning cis trans, right? But in that particular case, I was having two similar groups, right? Here, all the groups are dissimilar. Then, in order to define GI, or in order to write the nomenclature of these two geometrical isomeric form, we assign EZ nomenclature. For EZ nomenclature, what do? We assign priority to the groups. Okay. I'm having A and B, and here I'm having E and D. How do we assign priority? Let's see. First, I will move to this restricted center. I'm having two groups, E and D. Let us assume group E is more prior as compared to group D. Group E is more prior as compared to group D. So I will number it as 1 and this one as 2. Now I will move to this restricted center. And let us assume here also this group A is more prior as compared to group B. So A is more prior as compared to B. I will number 1 here and 2 here. Now I will check whether the similar prior groups are on the same side or not. 1 and 1 on same side, 2 and 2 on the same side. So such a system will be referred as Z system. If similar prior groups are on the opposite side, then it is referred as E nomenclature. Like this. The priority of E is more than that of D. So this one is 1 and this one is 2, right students? Here also A is more prior, so I will number 1 as A, and B, students, B will be having number 2 position, right? Now, similar prior group 1 and 1 on the opposite side, such a system is referred as E system. I hope you understood. Similar prior on the same side, Z. Similar prior on the opposite side, 1 and 1 on the opposite side, it is E. Now the second question is, how do we assign priority? Student, there is a rule to assign priority, and that rule is basically referred as CIP rule. So now it's time to discuss CIP rule to assign priority to the groups. CIP rules to decide seniority of the groups. It simply says priority is directly proportional to atomic number of the groups, atomic number of the atom directly bonded to the restricted center. Restricted center. First, we always need to check the atomic number. Let me try to explain you like this. I'm having fluorine here, and here I'm having chlorine. Which one is having higher atomic number? Chlorine. So chlorine will be a senior prior group. It will be numbered as 1, and here I will number it as 2. Now, the second question which may arise is, that if the first atom connected is same, then what should we do? Then move to the second atom and then check the atomic number. If the atomic number of second atom is also same, move to the third atom, and like that, and then only decide priority on the basis of atomic number. Now you can say, sir, if atomic number is same, suppose in case of isotopes, in that particular case, students will give preference to mass number. In case of isotopes, priority is directly proportional to atomic mass. But first priority is always given to atomic number. Okay. Now we have some more rules. It is assumed with increase in the bond order, the priority increases. So C triple bond C will be more prior as compared to C double bond C, and this one will be more prior as compared to C single bond C. Similarly, C triple bond N will be more prior to C double bond N. C double bond O will be more prior to C single bond O, like this. So we always need to give priority to the bond order. A triply bonded carbon-carbon bond is given more priority as compared to a doubly bonded. Now in case of ring, smaller the size of ring, higher is the priority. Higher is the priority. Okay, so these are the certain conditions to decide priority of the groups. I hope you understood this CIP rule. Now let's do some questions to understand it in a better way. Assign EZ nomenclature to the following. It's basically based on the CIP rule. Okay, let's do it. This one, I will move to this restricted center. I'm having a doubly bonded carbon and a triply bonded carbon. Which will be having more preference? A triple bond carbon will have more preference as compared to a double bond. So this one will be priority 1. This one will be having a priority 2. Now, here, C double bond O, C double bond O. I will move to the next atom. This carbon is directly connected to one more oxygen. Here it is directly connected to hydrogen. Between hydrogen and oxygen, which one is having higher atomic number? Obviously oxygen. So this one will be priority 1 and priority 2. Similar prior groups on the same side. So it is Z. Right, students? Let's move to the next question. 3-membered ring, 4-membered ring, or 5-member. 1, 2, 3, 4, 5-member ring. Smaller the size of ring, alkyl ring, higher is the priority. Okay, so this is a 3-member ring and this one is a 5-member ring. Which one will be more prior? This one. And this one will get priority 2. Now you can directly say, sir, here this 4-member ring will be more prior as compared to a 5-member ring. Student, here the first carbon is 3-degree carbon. The second carbon is a 2-degree carbon here, and here the second carbon is a doubly bonded carbon, right? And a doubly bonded carbon will get priority over the singly bonded carbon. So which one will be a more prior group? This one. So this one will be 1 and it will be 2. Now 1 on the same side. So once again it is going to be Z type of nomenclature. I hope you understood this one also. Let's move ahead. Coming to this restricted center, the groups connected C double bond O, S double bond O between carbon and sulfur. Which one is having higher atomic number? Tell me. Carbon, sulfur, sulfur. So this one is group 1 and this one will be group 2. Here, C triply bonded N and C connected to 3NH2. Student, even here also, this C triple bond will get preferred over this C NH2, NH2, NH2. So still here, this is priority 1 and this is priority 2. Similar prior groups on the opposite side. So this one is going to be E type of nomenclature. Next one. Let's assign EZ nomenclature to this particular compound. Okay. Mainly we need to assign EZ nomenclature about this restricted center. This one is most important. Okay. Let's do it one by one. Let us first of all talk about this particular carbon. Whether GI is feasible or not, the answer is yes. GI is definitely feasible. Similar prior groups on the same side. So this one is having Z configuration, right? Similar prior groups H and H on the opposite side, it is having E configuration. Or we can even write here, this one H, trans, this one H cis. Now the important is this one. If I look at this particular restricted center, methyl hydrogen, between methyl and hydrogen, methyl is more prior. So 1, 2. Now if I look at this restricted center, the next one, this one, I'm having the same molecular formula, everything is same, only the configuration is different, only the arrangement is different. Now which one will be more preferred, this one or this one? Student, in such cases, Z is always preferred over E. If everything is same, then Z is preferred over E. So this one will have priority 1 and this one will have priority 2. Now, similar prior groups on the same side. So this around this, I will have Z nomenclature or Z configuration. I hope you understood this particular example also. Now it's time to discuss the number of geometrical isomers in compounds having more than one geometrical centers. Okay, in that particular case, basically we'll have two different cases feasible. First, if the molecule is having similar ends or not, or if the molecule is having a symmetrical ends or not. Second, if it is having a symmetrical ends, then whether it is having a even number of geometrical center or odd number of geometrical center. So we are going to discuss all these cases, and in all such cases or in all such compounds, we are going to calculate the number of geometrical isomers. Let's see. First, compounds having the similar ends. So symmetrical ends is not there. Let me take one case. I'm having C double bond C, methyl here, hydrogen here, double bond C, ethyl here and methyl here. Are the ends similar? Not at all. In such case, student, the number of GI, number of geometrical isomers is always equals to 2 raised to the power n, where n is the number of geometrical centers. Geometrical center. Right, student? So how many geometrical centers are possible here? One here, one here. Two geometrical center. Two geometrical centers. So what will be the total number of geometrical isomers? 2 raised to the power 2. The number of isomeric form is going to be 4. I hope you understood this one. If the ends are dissimilar, and then whether check how many geometrical centers are there. 2 geometrical centers. Formula 2 raised to the power n. 2 raised to the power 2 here. Right? Let's move ahead. Compounds having similar ends. Students, here we will have two cases. Whether it is having a odd number of geometrical centers or even number of geometrical centers. If the compound is having odd number of geometrical centers, geometrical centers, then number of GI equals to 2 raised to the power n minus 1 plus 2 raised to the power p minus 1. Now what is p? P is basically here n plus 1 by 2. Okay, p is nothing but n plus 1 by 2 if it is having a odd number of geometrical center. Now second case, even number of geometrical center. Even number of geometrical center, then number of GI once again 2 raised to the power n minus 1 plus 2 raised to the power p minus 1. Formula is same, but the p value will change here. P here is simply n by 2. Why it's n by 2? Because n is even. I can simply, if n is 2, 2 by 2, 1. Here, this p cannot be fraction, right? That's why I'm adding 1. If n equals to 3, 3 plus 1 by 2, so p will be 2. So number of GI, if it is having odd number of center, 2 raised to the power n minus 1 plus 2 raised to the power p minus 1. Always, if n is odd, p is n plus 1 by 2. If n is even, p is n by 2 simply. Let's do some questions in order to understand this particular concept in a better way. Calculate the number of GI in all such cases. First one. This one is a geometrical center. This one is also a geometrical center. And this one is also a geometrical center. Are the ends similar? No. So is the molecule symmetrical? No, not at all. Now how many geometrical center? 3. If the ends are dissimilar, if the molecule is having a dissimilar ends, number of GI is 2 raised to the power n. N equals to 3, 2 raised to the power 3, it's equals to 8. In this particular case, let's discuss the second case. 1 geometrical center, 2 geometrical center, and 3 geometrical center, but similar ends with odd number of geometrical center. 2 raised to the power n minus 1 plus 2 raised to the power p minus 1. Now, what's the value of p here? N is 3. So, p is going to be 3 plus 1, that is 4. 3 plus 1 by 2, that's 2. So, it's nothing but 2 raised to the power 3 minus 1. So, it's 2 plus 2 raised to the power 2 minus 1. So, it's 1. It's nothing but 6. So the number of GI in the second case is going to be 6. Right, students? Now let's take the third case. 1 geometrical center, 2 geometrical center, 3 geometrical center, 4 geometrical center. Ends similar. Molecule is symmetrical. I can easily cut it, right? I can cut it from this carbon. 2 pi bonds this side, 2 pi bonds. Same group. Okay. Now here, the number of GI is once again going to be 2 raised to the power n minus 1 plus 2 raised to the power p minus 1. P is here n by 2, 4 by 2, so it's 2 only. Now, 2 raised to the power 4 minus 1 plus 2 raised to the power 2 minus 1. 2 raised to the power 3, that is 8 plus 2, 10. Number of GI feasible here is 10. So, this is how we calculate the number of geometrical isomers if I am having more than 1 geometrical center in a given compound. I hope you understood this one also. Let's move ahead. Students, now it's time to discuss physical properties of the isomeric form. Students, we have studied we are having 2 different isomeric forms, cis form and trans form. Now, which one is more polar? If I talk about the polarity of cis, the similar groups are on the same side. So vector will get added, right? So can I say in general, cis is going to be more polar as compared to trans. More is the polarity, higher is the boiling point. more is the polarity, higher is the solubility. Right, students? Let's talk about that. First, let's talk about dipole moment. This one, this configuration. This one is a trans configuration. In general, this is more polar. The dipole moment will be more. Right, students? The vector will get added. So dipole moment of cis is greater than that of trans. Right? Here the vector will cancel out each other. Second, more is the polarity, higher is the boiling point. Molecules having higher dipole moment have higher boiling point. It's mainly because of intermolecular force of attraction. Boiling point simply depends on polarity, or we can say boiling point simply depends on intermolecular force of attraction. Third one, solubility. More is the polarity, like dissolves like. So more is the polarity, higher is the solubility in water. Right? Fourth one, melting point. Student, this melting point depends on crystal lattice energy, and lattice energy depends on packing. Lattice energy depends on symmetry of the molecule. Now trans molecules are more symmetrical as compared to cis. So crystal lattice energy of trans is going to be more as compared to cis. So in general, not always, in general, melting point of trans is going to be more than that of cis. Right? Trans melting point more than that of cis, mainly because trans molecules are more symmetrical. Better is the packing, higher is the crystal lattice energy, larger will be the amount of heat required to break that bond, higher will be the melting point. Stability simply depends on crystal lattice energy. Stability simply depends on packing. Trans molecules are more symmetrical. Efficient packing, higher crystal lattice energy, more stable. Right, student? So student, this was all about geometrical isomers. I hope you understood geometrical isomers. Students, now it's time to discuss conformational isomers. We are having two different types of stereoisomers. One is configurational and the other one is conformational. Configurational isomers mainly arises because of difference in arrangement of groups around 3D space, and conformational isomers mainly arises because of different orientation of molecules in three-dimensional space. Now the question is, why there is different orientation? The different orientation is mainly because of free rotation across a sigma covalent bond. Not only CC, it can have an n sigma covalent bond. I can have free rotation. I can have free rotation between O sigma covalent bond. So across any sigma covalent bond, rotation is always free. Now, so across, can we read this statement? A sigma covalent bond undergo free rotation at room temperature. The question is, why will it undergo free rotation? Mainly because in order to release the strain, in order to increase the stability. If it will get confined at a fixed position only, strain will develop. So in order to release the strain, this free rotation is there. Right? Now, the second point, what do we mean by conformers, or what do we mean by the term rotamers? Student, let's try to understand it. This one palm is one carbon and the other one is the next carbon. These two carbons are connected via a sigma covalent bond. Now, what I am doing? I am rotating one of the carbon because across a sigma covalent bond there is free rotation. Now, can we say, as I am rotating it, I am getting different, or I am getting infinite number of orientations of molecules in a three-dimensional space. The infinite number of molecules which arises because of this free rotation is nothing but conformers or rotamers. Next question, are all the conformers or the rotamers, can we treat them as conformational isomers? No. Only those conformers or rotamers are treated as conformational isomers which are relatively more stable, or which is having minimum potential energy. One more point, conformational isomers are not the true isomers. Conformational isomers are not the true isomers. They cannot be isolated at room temperature, or they can even never be isolated. Right, student? Okay. Now, let us try to understand this free rotation across a sigma covalent bond. And if there is a free rotation, what will be the different possibility? What will be the different arrangement? Sorry, what will be the different orientation, not arrangement? And orientation is mainly because of free rotation. Okay. Now, I'm having a molecule like this. CH3, CH2, CH3. Right, student? Okay. Now, let's focus on this carbon number 1 and carbon number 2. Carbon number 1 and carbon number 2. These two carbons are connected by a sigma covalent bond. So we can have free rotation. Free rotation. Now I am going to draw one projection for this, and that projection is referred as Sohor's projection. Okay. What does this say? Let's try to see. Basically, I'm going to draw a line. This is carbon 1. This is carbon 2. On carbon 1, what are the atoms connected to carbon 1? One hydrogen, hydrogen, hydrogen. If I talk about carbon 2, the groups connected are 2 hydrogen atom and 1 methyl group. Methyl group, hydrogen, hydrogen. Right, students? Now, can I say we can have free rotation between carbon 1 and carbon 2? Between carbon 1 and carbon 2, I can have free rotation. Now, if I keep this molecule fix it. And now what I am doing? I am rotating this one. Can I say I can have an arrangement like this? C1, H, H, H. Can I say this methyl, can I keep it down? By rotation. If it will go down, this hydrogen will come this side, and this hydrogen will come this side. Can I say it is one of the orientations? Now how these two compounds will be related? They are nothing but the conformational isomers of each other. Right? If I again rotate it, I can come back to the original one. By rotation, I can come back to the original one. So these two, basically these two compounds differ in orientations. Right, students? And these two compounds are conformational isomers of each other. I hope you understood it. Now we have one more way of representation of this structure, and that representation is referred as Newman projection. Newman projection. Newman projection. Projection. Okay. How do we represent? Here, basically, the front carbon is represented by dot. Rear carbon is represented by a circle. Okay. Let's assume I am viewing it from this side. So can I say for me now this is going to be my front carbon and C1 is going to be my rear carbon. What are the groups connected to it? On this carbon, on carbon C2, the groups connected are CH3, H and H. Okay. So this one and this one. This is the front carbon and this one is rear carbon, students. Carbon. Now, the groups connected on front carbon are methyl and 2 hydrogen. And can I say it's basically in inverted Y shape? Methyl here, 1 hydrogen this side and 1 hydrogen this side. The same thing I am going to simply paste there. So, methyl and 2 hydrogen. Now, let's focus on the rear carbon. What are the groups connected? Hydrogen, hydrogen and hydrogen. And can I say again it is there in the inverted Y shape like this. 1 hydrogen here and 2 hydrogen like this. Okay, let's do that. I'm having on the rear carbon, I'm having one hydrogen connected here, one hydrogen connected here, and one hydrogen connected here. It's again in the inverted Y shape. Right, student? So this is one of the way of representation, and this representation is referred as Newman projection. This representation is referred as Newman projection. Okay. Now can I do one thing? Can I do the rotation? I have done the rotation in Sohas projection. And now what I have got? The methyl is down. So the front carbon is basically now in the Y shape and the rear carbon is in inverted Y shape. The same thing I am going to write there itself. Front carbon, rear carbon. Now the front carbon is there in the Y shape. So now it will be like this. Why? Okay. Here the groups connected are methyl down and 2 hydrogen up. Okay. So methyl here on the front carbon, 2 hydrogen. If I talk about the rear carbon, again it's there in the inverted Y shape, 1 hydrogen and 2 up and 2 hydrogen pointing down. Okay, 1 hydrogen up, 2 hydrogen down. Right? Now if someone say how these two compounds are related, they basically differ in orientations, they differ in free rotation. Because of this free rotation, I'm having different orientations, right? So these two compounds are conformational isomers. I hope you understood this one. So students, now let's discuss the conformational analysis of n-butane. Okay, I'm having molecular formula CH3, CH2, CH2, CH3. Now what I am going to do, I am going to discuss the rotation across C2, C3 bonds. Free rotation across this sigma covalent bond. Okay, now let us assume I am viewing it from this side. This is my front carbon, and this one is my rear carbon. Okay, rear carbon. Now let's draw it. Front carbon, rear carbon. What are the atoms connected to the front carbon? 2 hydrogen and 1 methyl group. Let us assume this is the methyl and now these two are hydrogen. Again, coming to the rear carbon, the groups or atoms connected are 1 methyl group and 2 hydrogen atom. Let us assume it is like this. 1 methyl group is here, 1 hydrogen is here, and 1 hydrogen is here. Right? This one rear carbon, 1 methyl, 2 hydrogen, rear. This one front. Okay. Students, now I am going to define a very important terminology referred as bond angle and dihedral angle. Are these two angles same? Not at all. Let's first of all try to understand bond angle. You can easily say you can easily identify bond angle. This particular angle, the angle between the two bonds of the same atom is nothing but the bond angle. So if here the bond angle is theta, I am saying it as a bond angle. This particular angle is bond angle. Now the next one is dihedral angle. What do we mean by dihedral angle? Dihedral angle is basically defined as the angle between any two bonds of adjacent atom. Okay, so this particular angle, CH3 and bonds of the rear carbon, 1 front carbon, 1 rear carbon. This particular angle is referred as, let's assume it's theta dash, then this is referred as dihedral angle. Dihedral angle. I hope you understood what do we mean by dihedral angle and bond angle. Dihedral angle is nothing but the angle between any two bonds of adjacent atom. Bond angle between the two bonds of the same atom. Okay. Students, now across as I am going to do the free rotation, let's keep one thing. I am keeping the front carbon fixed and I am rotating it. I am rotating the rear carbon. Okay. And I am rotating the rear carbon by 60 degree. Perfect. If I rotate it by 60 degree, What is the next conformer which I am going to get? I will get this one. The front carbon is fixed. The orientation of front carbon is fixed. CH3, H and H, right? If I talk about the rear carbon, now this methyl group will come down, will overlap with hydrogen. This hydrogen will come here, and students, this particular hydrogen will come over here. Right, students? This is one of the isomer. Okay. Now, next one. Again, I am going to do the rotation by 60 degree. Perfect. I am keeping the front carbon fixed. Basically, I am rotating the rear carbon. Front carbon fixed, rear carbon, I am rotating it. Right? And then the different conformers which I am getting, I am simply drawing it. Okay. And the dihedral angle is, basically I am changing the dihedral angle by 60 degree. Perfect. Again, I am having my front carbon fixed. CH3, H, H. Right, student? Now the rear carbon, methyl once again. This methyl will come over here. This one. Hydrogen will come over here. And this one more hydrogen will come over here. This is one of the orientations or one of the conformational isomers. Let's again change the dihedral angle by 60 degree. Perfect. What I am going to get? Front carbon fixed, rear carbon. I'm having methyl, methyl, hydrogen, hydrogen. Now this on the rear carbon, the methyl will come over here, hydrogen will come over here, and this hydrogen will come over here. Right, student? Okay. Let's once again change the dihedral angle by 60 degree. Perfect. I'm having a rear carbon, front carbon. Sorry, this one is the front carbon, rear carbon. Front carbon, methyl up, hydrogen this side and this side. Now, I have changed the dihedral angle by 60 degree. Here, methyl was here. So now this methyl will come over here. Right, student? Okay. So methyl will come over here. So now, if methyl will come over here, then this hydrogen will come over here and one hydrogen will be here. Next, once again change the dihedral angle by 60 degree. The next conformational isomers which I am going to get is this one. Methyl fixed, hydrogen and hydrogen. Now this methyl, the rear methyl will overlap here. Okay. This hydrogen will overlap here. And this hydrogen will overlap here. Right, student? So how many different conformational isomers till yet I have drawn? 1, 2, 3, 4 and 2, 6. Basically, I have moved it through entire 360 degree. 60 degree, 60 degree, 60 degree, 60 degree. And then I have obtained different conformational isomers. Now I am going to name these conformational isomers. They are relatively the stable conformers. Okay. Students, if the dihedral angle between two similar groups, is 60 degree, then that conformer is referred as, or that orientation we say it as Gauche. Gauche. So this one is nothing but Gauche. If the dihedral angle is 120 degree, here can I say almost the two different groups are overlapping. So basically such a conformers are referred as partially eclipsing. Partially eclipsing. Not two similar groups, but two dissimilar groups are overlapping. Right? Here the dihedral angle is basically 120 degree, theta dash. Theta dash was my dihedral angle. So in partially eclipsing, basically the dihedral angle is 120. Now, the two similar groups are exactly at anti with respect to each other. Such a conformer is referred as anti. 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 Okay, dihedral angle theta dash is 180 degree here. Next one, once again, the dihedral angle is basically I have moved across 240 degree. Once again, I am having two dissimilar group partially overlapping with each other. Once again, this conformer is referred as partially eclipsing. Partially eclipsing. Okay, next one. Two similar groups. Once again, the angle is 60 degree, or we can say the dihedral. I have basically moved across 300 degree. From here to here, I have moved across. Basically, I have rotated the rear carbon by 300 degree, right? The conformers once again obtained is, this one is referred as Gauchy. Why Gauchy? Because the dihedral angle between the two similar group is 60 degree, right? Okay, now if I look at this particular compound, the two similar groups are overlapping with each other. What is the dihedral angle? Dihedral angle is 0 degree. Such a conformer is referred as fully eclipsing conformer. So if I do the conformational analysis of n-butane, and if I change the dihedral angle by 60 degree, the different conformers which we get are Gauchy, partially eclipsing, fully eclipsing, and anti. Once again, I am repeating it: Gauchy, partially eclipsing, fully eclipsing, and anti. Okay, students, now why this orientation or why this different rotation is there? In order to release the strain, right? Obviously, if you look at this particular conformer, can I say more repulsion will be there because of the steric crowding? So students, now I am going to define few important terminologies, and these terminologies are related to strain. Basically, we have two different types of strain. One is referred as van der Waals strain and the other one is torsional strain. Let us discuss about that also. Students, now let's define first of all torsional strain. Okay, basically torsional strain is nothing but the strain which mainly arises because of interelectronic repulsion. So it mainly arises because of bond pair repulsion, and where this bond pair repulsion is going to be maximum in case of fully eclipsing structure, and even this bond pair interelectronic repulsion will be there in partially eclipsing structure also, right? So when the dihedral angle is 0 degree, 120 degree and 240 degree, in all such cases torsional strain is going to be there and it will be maximum in case if it is having a fully eclipsing structure. Obviously the bond pair repulsion will be less in case of Gauchy structure because the dihedral angle is 60 degree, right? So between the two bonds, now the angle spacing is more. Because of that, interelectronic repulsion will be less and it will be minimum in case of anti-conformer. The dihedral angle is 180 degree, right students? So if the dihedral angle is 180 degree, 60 degree and 300 degree, in such cases torsional strain will be relatively less, minimum in case of the dihedral angle 180 degree. Now let's discuss the next type of a strain, and that is van der Waals strain. Okay, van der Waals strain is mainly because of the steric crowding. It's mainly because of the presence of group, right? Let's define it. It is the repulsion between the two groups attached at adjacent bond, right? The van der Waals strain is maximum once again in case of eclipsing conformers and minimum in case of anti-conformers. While intermediate in Gauchy conformation, it's almost zero for hydrogen atom because hydrogen atom is relatively a very smaller group. So I have already told you van der Waals strain is mainly because of the steric crowding, whereas torsional strain is mainly because of the interelectronic repulsion. Now, can I say the strain is going to be maximum in case of a fully eclipsing structure. When the dihedral angle is 0 degree, in that case strain will be maximum, and if the strain is maximum, can I say potential energy will be more, stability will be less? Let's discuss that. Okay, students, let's discuss. If the dihedral angle is 0 degree, can I say it is a fully eclipsing structure? Fully eclipsing, right? And in case of fully eclipsing, we are having two strain, torsional max and van der Waals max. So can I say van der Waals max? Because of these two strains, potential energy will be more, stability will be less. So I'm having maximum potential energy in case of a fully eclipsing structure, right? Now I have moved by 60 degree. Now the dihedral angle is 60 degree. Here, basically what we'll have, Gaussian conformer. This one is nothing but Gaussian. In case of Gaussian, no doubt there is bit of torsional strain and there is also a bit of van der Waals strain, but the torsional strain is very less, and even van der Waals strain is also relatively less as compared to fully eclipsing and partially. So here the potential energy will be relatively less and the stability will be more. I have changed the dihedral angle once again by 60 degree. So basically now I have come to 120 dihedral angle. It is partially eclipsing structure. Here once again I will have torsional strain and relatively more van der Waals strain as compared to the Gaussian form, right? So can I say here the potential energy will be more, right? So here the potential energy is relatively more as compared to the Gaussian. So now you only tell me between partially eclipsing, fully eclipsing and Gaussian, which one is more stable? Gaussian, right? Once again I have changed the dihedral angle by 60 degree and now the dihedral angle is 180 degree. The two similar groups are exactly at 180. They are at anti positions with respect to each other. Can I say minimum torsional strain, negligible torsional, and minimum van der Waals strain, right students? So can I say here potential energy is going to be least and stability is going to be max. You can say between Gaussian and anti also. In case of anti, when the dihedral angle is 180 degree, the potential energy is less. Okay. Once again I have changed the dihedral angle by 60 degree. Now my dihedral angle is 240. So this one is representing partially eclipsing. Partially eclipsing. In case of partially eclipsing, no, we are having relatively torsional strain also and more van der Waals strain also. Because of that, the potential energy will be more, stability will be less. So this one was, fifth was partially eclipsing. Once again I have changed. Now the dihedral angle is 300 degree. From here I have changed the dihedral angle by 60 degree. So this config or conformer is nothing but Gaussian. Once again, so at 60 degree and at 300 degree the stability is going to be same because both of them are representing Gaussian. At 120 degree and 240 degree, once again the stability or the potential energy will be same because both of them are representing partially eclipsing structure, right? Now at 360 degree, once again I am having a fully eclipsing structure. Eclipsing structure, conformers. 0 degree, 360 degree, fully eclipsing, maximum potential energy. 180 degree, anti-conformer, minimum potential energy. After 0 degree and 360 degree, we will have dihedral angle 120 degree and 240 degree. More potential energy as compared to Gaussian and anti but less potential energy as compared to fully eclipsing. Right, students? This is the relative potential energy of all these conformers. If I talk about the stability, which one is more stable? Anti. Then we will have Gauchy. Right, student? Then we will have partially eclipsing. Partially eclipsing. Next one, we will have fully eclipsing. So the relative order, the most stable, anti, then Gauchy, then partially eclipsing, and least stable is fully eclipsing. It will have maximum potential energy, but it is in general, not always. There are certain cases where even Gauchy, stability of Gauchy dominates over anti. We are going to discuss those cases also. Students, we have studied that in general anti is more stable than Gauchy, but is it always true? No. There are several cases where the stability of Gauchy dominates over the stability of anti. And what are all these cases? The case where in Gauchy form, if I am having intramolecular hydrogen bonding, then in that particular case, the stability of Gauchy will dominate over anti. Let's see. If I am having CH2Z, CH2OH, if I am going to do, or if I am going to draw the conformers of this particular compound, and if Z is either OH, NH2, F, Nr2, NO2, acid and aldehyde, then in that particular case, if I will draw the Gauchy conformer, in Gauchy conformer, I will have intramolecular hydrogen bonding. And because of intramolecular hydrogen bonding, the stability of compound will be relatively more, right? So in all such cases, the stability of Gauchy will be more than the stability of anti. Gauchy is going to be more stable as compared to anti if in Gauchy form I'm having intramolecular hydrogen bonding. Okay, let's draw one more case. I'm having CH2OH, CH2OH, right? Student, let's draw the Gauchy and anti conformer of this particular compound. Okay, I'm having, let us assume this is my front carbon, rear carbon. On the front carbon, the groups connected are 1 OH and 2 hydrogen. OH, 2 hydrogen, right? I'm going to draw the Gauchy conformer. Now I'm going to move on the rear carbon. This is my rear carbon. On the rear carbon, the groups connected are OH and 2 hydrogen. Since it's a Gauchy, so 1 OH will be here, 1 H is going to be here, and H is going to be here. It's nothing but Gauchy 1. Gauchy. Dihedral angle is 60 degree here. Now, if I look at this particular compound, can I say I will have intramolecular hydrogen bonding? Del positive, del negative, I will have IMHB. IMHB stands for intramolecular hydrogen bonding. Now let's draw the anti-conformer. Front carbon, rear carbon. On front carbon, the groups connected are OH and 2 hydrogen. On the rear carbon, the groups connected are OH and OH and 2 hydrogen, right students? This hydrogen will come over here and this one will come over here. No doubt here the torsional strain and the van der Waals strain is relatively less. But here I'm having a very dominant stabilizing factor, that is IMHB, and because of IMHB, here also Gauchy will dominate over anti, right students? So in case I am having dipole-dipole interaction, ion dipole interaction, in all such cases, in case of dipole-dipole, dipole-dipole, ion dipole, stability of Gauchy will be more than that of anti. I hope you understood this one also. Students, now it's time to discuss the dipole moment or the observed dipole moment when a compound is showing or exhibiting conformational isomers. Okay, obviously the compound is having different orientations, so different orientations will have different polarity, will have different dipole moment. Now the observed dipole moment of the compound will be basically the summation of dipole moment of all the possible conformers, right, or all the possible stable conformational isomers. So for a compound CH2X, CH2Y, if I talk about the dipole moment, we define observed dipole moment mu observed is basically equals to summation of mole fraction of each conformers into dipole moment of each conformer, right? So can I write it as, let's talk about the conformers of n-butane or any other, right? So I'm having different possible conform, the Gauchy, partially eclipsing, fully eclipsing, and the anti. Let's write that. So can I say mu observed will be equals to chi of anti into mu of anti plus chi stands for mole fraction of Gauchy into mu of Gauchy, right student? Okay, plus chi of partially eclipsing into mu of partially eclipsing, right student? Plus chi of fully eclipsing into mu of fully eclipsing. Fe stands for fully eclipsing. Okay. Now students, in general, the mole fraction of fully eclipsing form and the partial eclipsing form is almost zero. It's negligible. So chi partially eclipsing and chi fully eclipsing is almost zero, tending to zero. So can I say these two terms will reduce to zero, this one and this one. So what will be the mu observed? It's nothing but chi anti into mu anti plus chi Gauchy into mu Gauchy, right? Mu observed is going to be chi anti, that is mole fraction of anti into dipole moment of anti plus mole fraction of Gauchy into dipole moment of Gauchy. Now one more thing, if let us assume x equals to y, if the groups are similar, then in that case can I say mu of anti will be equals to 0. The vector sum is going to be 0. The net vectors, they will cancel out each other. So can I say even this one will also reduce to 0? In that particular case, mu observed is always equals to chi Gauchy into mu Gauchy. Right students? I hope you understood it. This was all about the dipole moment. Let us move ahead students. So students, now let us discuss the conformational analysis of cycloalkane. Conformational isomers. Conformational isomers of cycloalkane. Student, if I talk about this cycloalkane, you will say, so in cyclic compound there is restriction in rotation. So how we can have conformational isomers here? Because conformational isomers are mainly obtained by rotation around CC sigma bond, right? Student, here we get conformers not because of rotation but because of flipping of structures. Students, while talking about this conformational isomers in case of cycloalkane, mainly we are going to discuss only one case, and that is the conformational analysis of cyclohexane. conformational analysis of cyclohexane. Okay. Having the molecular formula C6H12. Student, because of flipping, this cyclohexane is having different conformers. So let's see the structures of these conformers and let's see the stability of these conformers. Let's start, or let's do the conformational analysis of cyclohexane. So the different conformers which we have is, the first one is the chair form. Next one, half chair, then half chair, then we can have boat, then we can have twisted boat or twist boat, then we can have inverted chair. If I talk about the relative stability, the most stable conformers are chair form and inverted chair form. These two conformers have the same stability. Students, whenever we draw the structure of cyclohexane, most of the time we draw these structures only. Why? Because it is the most stable conformer of cyclohexane. Why it is more stable? Here basically we are having a perfect tetrahedral geometry. There is no angular strain here. Because of 0 degree angular strain, this structure is relatively, or this conformer is relatively more stable. Chair form or inverted chair form. Whenever anyone say you draw, they will give you a certain compound and there certain cyclohexane compounds, and they will say you to draw this compound. Always draw it in a chair form or inverted chair form. It's the most stable conformers of cyclohexane. Okay. Next, if I talk about the relative stability, the least stable is half chair, right? These two, basically half chair is the least stable one. Then students, if I talk about twist boat, then we have boat. Between boat and twist boat, it seems twist boat is relatively more unstable. It is having more potential energy, but students, generally twist boat or always twist boat is more stable as compared to boat, right? So what is the relative stability order? Most chair, then we will have twist boat, then we will have boat, and the least stable is half chair, right? So for us, the most important conformer is the chair form. So we are going to discuss all about chair form itself. Students, now assume these two conformers as the chair form and the inverted chair. Let's assume this one is the chair form, and this one is inverted chair. Let's first of all focus on this chair form, right? Okay. Carbon having a tetrahedral geometry, sp3 hybridized. So obviously each carbon will be connected to 4 bonds, right? Okay. 2 bonds already there in the cycle. So I will have 2 more bonds, right? Now we say this bond as the axial bond and this one as equatorial bond. Student, I am giving you a simple trick. In the chair form or even in the inverted chair form, if the vertex is pointing up, axial up, vertex pointing down, axial down, vertex up, axial up, vertex down, axial down. Okay, vertex down, this one will be the axial. Between axial and equatorial, the bond angle is 109. So if this one is going down, it will go up like this, right? Okay. Here, vertex up, axial up, equatorial down. Vertex down, axial down, equatorial up. Vertex up, axial up, equatorial down. Vertex down, axial down. This bond is the axial bond. So this one is going to be the equatorial. The bond angle is 109, right? Okay. So this is how we represent axial bonds and equatorial bonds in chair form, right? Now students, we know chair form and inverted chair form always exist in dynamic equilibrium with respect to each other. They are having the same stability, right? They are having the same stability. So there is a continuous flipping. If I flip this chair form, I am going to get the inverted chair. Now, if we do the flipping process, the axial bond becomes equatorial in the inverted chair, and the equatorial one will become axial. Okay, we'll try to understand it with one example also, but first let's see how do we do the flipping process. Let's number it. I'm having 1, 2, 3, 4, 5, 6. Let's assume I am doing the flipping like this. Like this. Okay. So now this 2 will come down. So here I will have 2. Right, students? Now this 3 will come here. 4, 5, 6. This 1 will come here. Right? Now the axial, no doubt here also the axial equatorial. Now I can simply axial equatorial, axial equatorial, axial equatorial, axial equatorial, axial equatorial, right? So this is how we do the flipping. Students, now one thing we need to remember while doing the flipping process, basically the geometry of the molecule does not change. If a particular compound is going into the plane, even after flipping also it will be in the plane only. If it is down, after flipping also it has to be on down only. Let us try to understand this with one example. Let's assume here at the equatorial position I am having a methyl group connected on carbon 1. This one is carbon 2. Sorry, on carbon 2 I am having a methyl group connected. So now as soon as I do the flipping, where is this methyl? It's down the plane. Axial up, equatorial down here. So I will move to carbon 2 and here the methyl will again come to the down position. Now what you have observed after flipping, the group which is present at equatorial becomes at or comes at axial position. So if a group is present at axial position in chair form, it will come at equatorial position in inverted chair. Okay, now let's do the further analysis of the conformational isomers of cyclohexane. Students, I am given a compound methyl cyclohexane and someone say you draw the most stable conformer of this methyl cyclohexane. Which conformer you are going to draw? The chair form or the inverted chair form? Let's draw it. I'm having the chair form, okay, right? And then I will have the chair form like this, right, students? Now the problem is, where do we put this methyl group? Obviously we can put it on any carbon. I can put here, I can put on carbon number 2, 3, 4, 5, 6 on any carbon, right? The position is not confined. Basically it's methyl cyclohexane. But now the problem is whether it will come at equatorial position or axial position. Student, whenever we have to do the substitution, always remember the bulkier groups always occupy equatorial position. So I will place it at equatorial position. Now you can say why. Basically, students, in this chair conformer, if I will place the bulky group at the axial position, then I will have 1,3 diaxial repulsion. Diaxial repulsion. Right? Basically, if I am going to draw the Newman projection of this compound, then what I will observe, or what we may observe, we will, this particular compound, if this methyl is placed at axial position, we will have 1,3 diaxial repulsion. In order to avoid that, the bulkier group is always placed at equatorial position. Once again, I am repeating, the bulkier group is always placed at equatorial position, either in the chair form or even in the inverted chair form. The first substitution of the bulkier group, you need to place it at equatorial position, right? Okay. Students, let's discuss one or two more examples in order to understand the position of substituents in this conformer of cyclohexane. I'm having a cyclohexane, and at position 1 and position 3, two groups are present. One is CMe3 and one is CH3. Which one is more bulkier? CMe3, right? So if I am going to draw this chair conformer, let's draw it, or let's draw it in a better way, right? I'm having this one, these two parallel lines, then this one will go down here, it will come like this, and then I will have this one parallel to this one, and then, right? So this is the chair form. Now I need to place these two groups in the chair form. Students, always keep it in mind, whenever you have to do the substitution, always do the substitution of bulkier group first. And where you will place it? You will place it at equatorial position. Let's assume this one is the axial bond, so this one is going to be the equatorial. So I am placing this CMe3 here, right? This CMe3 here. Now 1,3 position, so I can move in this way, second and third. So I can place CH3 here, or I can place CH3 here. Once again, I am going to place this CH3 at which position? Which position? Equatorial position only, because here the geometry is not defined. It's not said that basically they are at this position or transposition with respect to each other. Here geometry is not decided, geometry is not defined. So here also I am going to place this methyl group at equatorial position itself. So if someone says draw the most stable conformer of this particular compound, it is going to be the most stable one. If I place the bulkier group at axial position, then it will face 1,3 diaxial repulsion. Stability will decrease. So student, always remember, bulkier group is always placed at equatorial position. Now let's discuss one or two more examples. So students, now let's do one or two questions related to this conformational isomers in cyclohexane. The question is, draw the most stable conformer of this 1,3 dimethyl cyclohexane. Okay, let's first draw the simpler cyclohexane geometry. It's like this, right? This 1,3, one methyl here, since it's on the wedge, so the other methyl will also be at the wedge itself, right? Now this is cis 1,3 dimethyl cyclohexane. Now I am going to draw the chair conformer of this one, because only the chair conformer is relatively more stable, right? Okay, now this one and parallel to this, right? So this is the chair conformer. Student, now here we need to define geometry also. So now let me define geometry here. Axial, equatorial, axial, equatorial, axial, equatorial. Here axial is up, this axial is down, up down is basically trans, up is cis. So if one group is placed here and if one group is placed here, they will be cis with respect to each other. Up cis, up cis, up down, trans, down cis, down up trans, right? I hope you understood this. Now it is cis. Now I have already told you the first group is always placed at equatorial position. Okay, so what I am going to do, I am going to substitute this methyl group here at the equatorial position. Now is it up or down? This equatorial bond is pointing up, and now if it has to be cis at 1,3 position, so this one, either this one can be the 1,3 position or this one can be the 1,3 position, right? Now here this methyl is going up, so 1 2 3, here also the methyl has to go up only, right? So this is the most stable conformer of cis 1,3 dimethyl cyclohexane. Equatorial, right? Here also it is occupying equatorial and both of them are up. Now students, now let's do one more question, and now we are going to draw the trans configuration. Okay, draw the most stable conformer of first trans 1,3 dimethyl cyclohexane, and the second one trans 1,2 dimethyl cyclohexane. This already we have drawn, so now let's focus on the trans part. Perfect. Trans 1,3 dimethyl cyclohexane. This is cyclohexane. Now I am having two methyl group and they are at 1,3 position with respect to each other. So one methyl group present here and the other methyl group will be present here, right? So it's nothing but trans 1,3 dimethyl cyclohexane. Now I am going to draw the chair conformer of this one. Right, student? This is going to be the chair conformer, right? Now this one. Okay. Now, first I will place one of the methyl group at equatorial position because I need to draw the most stable conformer. So now let us assume I am substituting this methyl group, this one here, methyl. Now both the methyl group are at anti position. So if one of the methyl group here, if it's down, the other one has to be at up position, right? Now, no doubt it is at equatorial position. I will move to the third carbon. 1, 2, 3. This one down. Here, this bond is pointing up, right? So I need to place this methyl group at axial position. You will say, sir, you only told we should always substitute the groups at equatorial position in order to avoid 1,3 diaxial repulsion, and now you are only substituting this methyl at axial. Student, basically I am forced to place this methyl group at axial position. Why? Because the geometry is defined here. We cannot change the geometry of a molecule, right? So this is going to be the most stable conformer of trans 1,3-dimethyl cyclohexane. One group is placed at equatorial, and at third position one of the carbon is placed at axial. Why? Because it is down, then the other one has to be up. You will say, sir, let's move in this direction. Okay, here also it is down, so this bond will be the up, and the vertex up, axial up, so this bond is once again the axial. So anyhow, if it is trans 1,3-dimethyl cyclohexane, student, or 1,3 substitution in trans, one of the group will be at equatorial and the other group will be at axial. The bulkier group will be at equatorial, the smaller or less bulkier group will be at axial. I hope you understood this trans 1,3 configuration. Bulkier at equatorial, less bulkier at axial, because the geometry is defined here, right? Let's move ahead. Trans 1,2-dimethyl cyclohexane. Let's draw this structure. I'm having 1,2-dimethyl. So one of the methyl group is placed here and the other methyl group will be placed here. Now let's draw the chair form. Right, student? This is going to be the chair form of this particular compound. Now let's put one of the group at equatorial. First of all, first group is always placed at, or the bulkier group is always placed at equatorial. No doubt the steric crowding is same, alkyl size is same, but still I will place the first group at equatorial. Next one, I need to move to the second position. Now they are at trans. In chair conformer we will have up down configuration, right? One down, so other up. Now this one is pointing down, so other has to point up. I'll move to this carbon. Here axial is going down and equatorial is going up, and we need, already it's a down configuration, so I need to place this methyl here, right? So students, in trans 1,2 substitution, both the groups are present at equatorial position. Trans 1,2, both groups at equatorial position. Equatorial position. I hope you understood it. Okay, if let us suppose if CME3 is placed here, what will you do? You will first substitute CME3 here and CS3 here then, right? I hope you understood how to draw the different stable conformers of cyclohexane or substituted cyclohexane. Student, so this was all about conformational isomers. Students, the next topic that we are going to discuss is optical isomers, but it is not possible to complete this optical isomers in today's lecture, and I want to finish it in a single shot. So what I am planning to do, either I will combine it with reaction mechanism, that is the lecture number 3, or will put a separate lecture for this optical isomer. So students, that's all about today's lecture. If I talk about today's lecture, mainly we had discussed all the structural isomers starting from chain isomers, then we discussed positional isomers, functional isomers, metamers, tautomers, ring chain isomers, right? Then we move towards stereoisomers. In stereoisomers, we started with configurational isomers and conformational isomers. In configurational isomers, we had two types of isomers. One is geometrical, other one is optical. Geometrical we have thoroughly covered. This optical is still remaining, but you don't need to bother. Either I will put it in extra class, or we will combine it with the third lecture, that is the lecture on reaction mechanism. There we have to cover this basic strength also, so you don't need to bother at all, you don't need to panic. Optical isomers is one of the most important subtopics. So what I have decided, let's not rush. We'll finish optical isomers in 1.5 or 2 hour lecture separately. You don't need to bother about this optical isomerism at all. I simply request you to go through this particular lecture thoroughly and attempt all the PYQs of the topics what we have covered today. So thank you students for watching the lecture. Thank you once again.